Our first speaker is here. Yes, okay. Yeah,
they should be able to. They should be able to share their screen.
Yeah, Wei, do you want to just check if you can share? Okay, that's good.
Good.
Oh,
Yeah,
you're
you
muted.
can stop. Oh,
Just make sure.
Thanks. Yeah,
Okay.
just thank you for
Okay.
just realized I'm muted. Can you guys see my screen and hear me well?
yeah, you can stop sharing for a minute. We'll just go through the logistics and then we'll start. But
Okay.
okay, I guess we'll start now. So welcome to the Climate Variability and Change Working Group session. So I'm Isla Simpson, and here with Sarah Larson and Aishu Hu, the other co-chairs of the working group. So we have a great lineup of talks, and in the middle, kind of at the end of the first part, we want to have lots of discussion about the simulations that we're going to propose for the next computing allocation. So for the speakers, it's a 12-minute slot, so 10 minutes for talking, and then we'll have a couple of minutes for questions and changeover, and we'll give you a warning at 8 minutes. So we'll just get started, and I'll hand it over to Aishu, who's going to chair the first session.
Okay, now the first speaker is Wei Liu. He will talk about the stratosphere and the troposphere ozone effect on the Southern Ocean warming. Okay, Wei, the story up.
Thank you very much, Aisha. Okay, so I'm sharing my screen. Okay, so thank you very much for having me here. I'm Wei Liu from UC Riverside. So today I'm going to talk about disentangling the impacts of stratospheric ozone depletion and tropospheric ozone increases on Southern Ocean interior warming. So this work, I collaborate with Makila Haglin and Remil Cheka Garcia, Shuwei Li, Nathan Gillett, Kovei Lu, Xuebin Zhang, and Neil Swart. Okay, so first, let's look at the historical ozone changes. So here I'm showing two panels. The left is the prescribed ozone change for CESM4 and the CESM1 and on the right would be the input for CESM6. So the figures I'm showing here is the prescribed ozone change in the two generations of models, and basically is the annual and zonal mean fractional change. So in ozone forcing, on the right, I put the formula. Basically, it's ozone in 95 to 99 minus 55 to 59, normalized by the 55 to 59. So from this figure, we can see the depletion of tropospheric ozone, especially in the South Pole region, in the high latitudes, in high elevation. And that would be the well-known stratospheric ozone hole, which has been observed in the past few decades. On the other hand, if we look at the low level in the troposphere, and we can see the increase of ozone, the increase of tropospheric ozone. So now the scientific question is that, what will be the ozone impact for our climate system? Because it has been well studied for the ozone impacts on the many things, like the atmosphere circulation, and also the radiation imbalance at the TOA. However, relatively less attention has been put on for ocean, especially if we think about the ocean heat uptake, especially in the Southern Ocean. So that is a very important issue, and we want to look at. So there have been studies talking about the effects of stratospheric ozone depletion. For example, in Swart et al. 2018 Nature Geoscience paper. And however, one missing point would be like, what would be the impact of the tropospheric ozone increase? Because we can see this tropical ozone increase is very notable signal from the figure here. So the question would be, what would be the impact of tropospheric ozone increase on Southern Ocean heat uptake and Southern Ocean warming? So what we use would be the CESM5 and CESM6 ozone single forcing experiments. So for those who are familiar with the experiment, basically in either CMIP5 and CMIP6, and we have the single forcing. Basically, we only force the model using the historical changes of ozone, but for the other factors were set to pre-industrial level. So on the left, I'm showing the CMIP5 result, and on the right would be the CMIP6 results. So the top panels show the annual and zonal mean, zonal winds change during 1955 to 2000, and the bottom two panels shows the annual zonal mean ocean temperature during this period. So let's first look at the CMIP5, and we notice in the CMIP5 models and the experiments were forced by total ozone change, so which includes both stratospheric and tropospheric ozone. However, it's different for the CMIP6 models, in which we only have the ozone forcing from the stratosphere. So for CMIP6 experiments, it's forced only by stratospheric ozone change. Okay, so let's first look at the ionosphere, and we can see a polar intensification of the wetly range. So here the contour overlapped is the pre-industrial climatology wind fields. So we can see this very robust feature for the polar world intensification of southern hemisphere wetly range, which has been reported in many previous studies. And also if we compare CMIP5 and CMIP6, and we can see, yeah, there are not too much differences. Difference we can so we can see from these two panels. However, situation will be different if we look at the ocean. So for the ocean, we can see in the Southern Ocean, CMIP5 model simulates a very strong warming in the interior region. And however, in CMIP6, the warming is much weaker. So there could be many reasons why we can get these different results, right? So first, the ozone forcing, we can have some slight differences between the CMIP5 and CMIP6 if we look at the previous slide. The second, and we can see there would be different models. For CMIP5, and I have these four models, so the figure shows multi-model mean over these four models. But for CMIP6, they are totally different models. So these different models could have different impact because we are not quite sure the model will have different response to the ozone forcing. But this figure can give us some implication, like one missing part or one important factor would be the stratospheric ozone, because if we look at CMIP5, and we can see it's forced by both stratospheric and tropospheric ozone. However, only stratospheric ozone is input into the CMIP6 simulations. So we are wondering whether the tropospheric ozone can explain the difference between the Southern Ocean warming and heat uptake. So to test this hypothesis, and we are using Cam Esm5. This is the CMIP6 error model. So for this model, and we have the data available from the CMIP6 archive with two suits of experiments. So the first suit would be the total ozone forcing, stratospheric plus tropospheric ozone. The result shows in the left. And another suit of experiment would be stratospheric ozone only, that is consistent with other CMIP6 models. So the result is shown in the middle. And on the right would be the difference between the first two, so which indicates the impacts of tropospheric ozone change. Okay, so similar to the previous ones, and the top panel showed the annual and zonal mean zonal winds. And so that's the difference between the 1955 to 2000 and pre-industrial. So we can see the contour indicates pre-industrial climatology, and also the shading where we have the dotted region, which means it's not statistically significant. So if we look at the top panels, let's look at the winds, and we can see a very robust polar world intensification for the total ozone forcing. So that's very similar to the previous result. And for the stratospheric ozone, we can still see this polar world intensification of southern hemisphere westerly winds. And the difference for the tropospheric ozone impacts, we can see there is upward intensification in the upper levels, and at lower levels, we can see a signal of polar world intensification of westerly winds. So it's worth noting that as toward to the surface and the magnitude of wind change is comparable between stratospheric ozone change and tropospheric ozone change. So that's for the top panels. Then let's look at the bottom panels, which shows the zonal and annual mean ocean temperature change during 1955 to 2000. So we can see very robust warming occurs in both stratospheric ozone simulation and also the difference, which indicates tropospheric ozone impacts. So from this figure, to summarize, we can see Southern Ocean interior warming is induced by both stratospheric ozone depletion and tropospheric ozone increases. Then we also look at the ocean heat content change. So here I'm showing the time series for all these experiments. So first, let's look at the result from Cam Esm5. So let me walk through you from these figures. So if we look at this, this very thick blue curve, so that is the result from the this model for the stratospheric ozone only experiment. And meanwhile, we can see this dark purple curve, which indicates ocean heat content change in the historical run for this model. So then if we compare these two curves, we can see the total ozone change contributes about 1/3 of the net historical ocean heat content increase. That is within upper 2,000 meters between 30 to 60 degrees south over 1955 to 2000. So that's the first result. And then we want to participate the contribution from both stratospheric ozone and tropospheric ozone, which has been illustrated in the left panel. So that's the blue curve I just mentioned. And then the red curve is the ocean heat content change due to stratospheric ozone depletion, while the black one is the difference. Thank you. Between the two. So we can see the 50% is from tropospheric ozone increase, but 40% is from stratospheric ozone depletion. And also the result is consistent with simplified model simulation. So what will be the physical mechanisms? So we decompose the total temperature change into the species change and heavy change. So on the left, I'm showing the species change for the three total stratospheric and tropical ozone forcing. And on the right is the heavy part. So very clearly, and we can see for the species, for the stratospheric ozone, it's mainly contribute from the species change, but on the other hand, from the tropospheric ozone increase is mainly through the heavy change. And then we look at the surface heat flux and surface wind change, and it's consistent with our results. Okay, so due to the time, I just gone to my conclusion. And so basically we can see stratospheric ozone and tropospheric ozone can both contribute to Southern Ocean warming. And the tropospheric ozone is very important and it's more than an air pollutant. It's as greenhouse gas, it can be very important for the global warming, especially for the ocean heat uptake. So thank you very much. And I would like to thank the support from the NSF and Sloan Fellowship. And if you are interested in more information, and here is our paper. Thank you very much for your attention.
Thank you, Wei. If there's a quick question, you can ask now. Otherwise, we move to the next talk. Okay, Ella.
Yeah, sorry, just a clarification. I'm not an oceanographer. I didn't, what does heave mean? And I didn't follow the terminology.
Thanks, Ella. Due to the time, I just cut off the information.
Yeah.
So here, basically, you can understand like the wind-driven part, like the wind-driven, like my pumping, kind of depress or uplift the thermocline. So by this will create the temperature change. On the other hand, for the species, it's something like the subduction through the middle water or intermediate water. Basically, if we have the surface heat flux or freshwater forcing, so the temperature can propagate along the epicenter.
Thank you.
Thank you.
Okay, now we move on to the next talk. Will be given by Carlos on the hydroclimate change in Caribbean using CESM. Carlos, go ahead.
Great. Let me share my screen here. Can you all see the screen?
Oh, yes.
Okay, great, wonderful. Well, hello everyone. I'm Carlos Martinez. I'm an ASP postdoc with CGD and M3, and my presentation is on the seasonal hydroclimate of the Caribbean under various CESM as well as some CMIP6 models. So why the Caribbean? Well, I looked at the Caribbean and its observed hydroclimate, and one of the reasons why it's such a complex region, perhaps for models, is because it's not a homogeneous region. You have different hydroclimates in different parts of the Caribbean. For example, in the Northwestern Caribbean, you have two peaks, the first being the early rainy season from mid-April through mid-June, and the late rainy season, which for several Caribbean regions is the largest portion of rainfall across the hydroclimate. But if you look at the Eastern Caribbean, so over the Lesser Antilles and Barbados, you don't see an early rainy season. And other regions have different amplitudes or magnitudes of each seasonal component of the rainfall cycle. In addition to this, it's a rain-fed region. Many stakeholders rely on rainfall for their socioeconomic needs, and the climate and the dynamics in this region is important for other regions such as the Pacific Basin as well as the southeastern United States. So seeing the complexity of the cycle and the mechanisms, which I'll explain later, that correspond to and influence the hydroclimate, I wanted to look at global circulation models like the CESM model suite to simulate the rainfall cycle and see how well they do compared to my observational framework that I did. Do the models, for example, perform better over ocean-only spaces versus land where there's less complexity, such as topography, since we're dealing with islands? Are there biases in a specific subregion of the Caribbean, or is this general to the entire basin? And is there a relationship between model resolution, especially since we're dealing with islands, versus between low versus high resolution models? And so I looked at several models. The top, or this box on the right, shows all the models that I used. There are several CESM models, such as the Lens 1 and 2, as well as their GOGA or Amip runs, and the IHES high resolution CESM model as well. I also looked at the CMIP high res MIP models, which the only difference for each model group is just the resolution, looking at their low versus high resolution versions to get into that question on the resolution component of this study. And then looking at observations, I used several gridded precipitation data sets to have an observational estimate, as well as using ERA5, which will also be used as the benchmark observation for the dynamical variables that I'm using in my analysis, as well as other station data. So for the methodology, I looked first at precipitation scatter plots between ocean only and land only precipitation totals to see if there are differences there. And then I regressed using all of the models, several dynamical variables that I know from my previous work to inform the hydroclimate in the Caribbean onto the precipitation indices across the different subregions. Then I looked at scatter plots related to where I'm finding the model regression and those intermodal differences to be highest in the correlations. Looked at spatial averages of those to produce dynamical indices versus those precip indices. And then finally, for the sake of time, I'm just going to look at one seasonal component of the rainfall cycle, the early rainy season, which is important for the onset, the start of the rainy season, as well as the growing season for many stakeholders. So just for clarity, these are the different subregions of the Caribbean. And for the first example, I'll be looking at the Northwestern corridor, and this is like the spatial grid box that I'm looking at. But there are several other subregions that I have looked at for the analysis. So the first part is looking at scatter plots between land versus ocean only precipitation. You can see here in the legend all of the models that I used. The ones in black are the observational data sets, and then the low res models are in blue and the high res models are in red. And what you see, generally speaking, is that most models underestimate land only and also ocean only precipitation. We do see some differences, especially when I'm looking from model group to model group. I do see that the high resolution models tend to show values that are closer to the observational estimates than their low resolution counterparts. So this is just an example here, the high res, as well as the Amip run from high res CESM. And then just to highlight this, we see this pattern across most of the models. There are a few cases where we see some biases, like for example, with MPI with an ocean bias there. But I do see this generally speaking across all of the subregions for this season. In addition to that, I do have the large ensembles and their spread within the individual members, and comparing, for example, CESM2 with the CESM2 GOGA runs, you do see that the Amip runs show more precipitation, but under a same land-ocean ratio, and that's what the dotted lines show, where we also see the model show a less ratio than the ratios that we're seeing between land versus ocean in the observational spread. So if I look at another region, for example, we see a similar case in the spread between the blues and the reds. The only difference is the Amip runs showing more precipitation than the fully coupled runs from the CESM models. So it's clear here that there seems to be an underestimation, generally speaking. Why is that? And it's clear that there seems to be a separation between the high res and the low res models. Could dynamics be a role in that bias, in that dry bias? And so going into the model spatial regressions, we see some patterns here that might suggest this. So what I'm presenting here is an example looking at May precipitation regressed onto Central Caribbean May precipitation index. On the left is the regression beta coefficient, and on the right is the correlation coefficient from that model-based regression. And what you see is that there are patterns here that go well beyond the Caribbean basin. You have, for example, this couplet over the Atlantic and Eastern Pacific basins, and this widespread of precipitation or positive values in the Caribbean basin off to the tropical North Atlantic. And when we look at the correlation of that plot, we see it well defined. And so this is where we will see most likely those intermodal differences. But what are these mechanisms, right? So in my observed framework, there are three main facilitators of moisture convergence that I found for the hydroclimate in the Caribbean. One is over the western flank of the North Atlantic subtropical high, and then the eastern and Atlantic branches of the intertropical convergence zones. During the season prior to the early rainy season, so in this case for the hydroclimate in February, looking at total moisture flux and convergence, we see the high is very strong, and with it divergence and easterly winds across the Caribbean corridor. We see some patches of green right over the islands. That denotes perhaps the small scale convergence over the islands, but generally speaking, we see this widespread divergence. When we move into the month of May, or the beginning of the early rainy season, we see a lot of changes here. We see the divergence band weaken across the Caribbean basin. The easterly winds become southeasterly, so we're having an influx of moisture from the tropics onto the Caribbean basin, and the high produces on its western side this convergence band that moves northwest into the northwestern Caribbean, alongside the ITZZ bands migrating northward. And so this is why we see for the early rainy season and the transition from the winter dry season. So when I look at the regression of other variables that I know are to inform the hydroclimate in the Caribbean, we see patterns that resemble these large scale features. So SLP with the zonal mean removed, showing more precipitation with lower SLP values. For SSTs, we see warmer Caribbean Sea and the southern portion of the North Atlantic. And under the zonal winds, low level winds, we see more westerlies or weaker or more easterlies, which denote a weakening of the circulation itself, and consequently, thus a weaker high for more precipitation across the Caribbean. And this resembles my paper earlier from the interannual variability of the early and late rainy seasons, where these anomalous patterns resemble the winter-induced North Atlantic oscillation, where under a wet phase, a negative NAO induces these anomalous signals. So there's something here at play that the models are going to have intermodal differences with. So just to then conclude here, I took spatial averages of these various dynamical variables between, for example, sea level pressure anomalies with the zonal mean removed versus the land precipitation totals over the Central Caribbean for the 2 months. And we see very clearly this relationship where you have lower SLP and more precipitation compared to the observations, all of which have the SLP value from ERA 5. In addition to that, we see the same story across all of the subregions of the Caribbean as well. So this is not defined just for the Central Caribbean. And then the last slide here is to show the longitudinal center of the subtropical high using a metric that I used, where we clearly see for most models have a westward shift of the center of the high than what ERA 5 is showing. And if you have a westward shift, you're going to have that influx, more influx of divergence easterlies across the Caribbean, which might be a reason for the dry bias that we see during the early rainy season. And again, we see this simultaneous across all of the subregions as well, where all the models show the high to be further westward than what we see in the observations. And there is some suggestion of differences between the high versus the low resolution in that case as well. So just to summarize and conclude, I performed several simulations of the cycle and the mechanisms under a suite of these models. I do see that most models underestimate the land and ocean precipitation, where you would find, less complexity, for example, because there's no land, right? So interestingly, looking at the model regressions, they suggest that perhaps the dry bias is in part due to a stronger and or westward shift of the high, which causes the enhanced easterlies and divergence, and potentially also a southern displacement of the ITZZ as you have a stronger high over the North Atlantic region. I do see a difference between the high res versus the low res models, which might suggest that perhaps the high res perform better over the dynamical mechanisms and the estimates. But to conclude here, I will be looking at some of these other variables like Mariana wind component and look at these other regressions indices and the other seasons, the midsummer drought and the late rainy season, to see if there is consistency there. And so with that, I conclude my presentation. Thank you so much.
Thank you. Very interesting. And is there any question? I have a question to ask you. Is right now, it seems like you just look at the mean state. And do you look at the decadal or multi-decadal time scale variability? It's going to be the same, or it will be different?
Looking at the multi-decadal variability, is that correct? What you?
That's right. Yeah.
I haven't looked at decadal or multi-decadal scales to see if there are differences here. What I did find with the anomalous patterns or in the model regressions was there appear to be similarities between my anomalous plots that I showed from a previous study that looked at the interannual variability in the NAO, inducing those signals. As the early rainy season is primarily like changes between its dry and wet state is due to how the NAO how it works during the winter time preceding the early rainy season, and then you see a persistent SLP and SST signal from ocean memory that continues on. But I'd be interested in looking at those other timescales, as those likely do inform the hydroclimate in the region as well.
Thank you. If there's no further question, we move to the next talk. Next talk will be given by Amir.
I'm here. Hello.
Okay.
I'm sharing my screen.
Yes, you can go ahead and share your screen. By the way, I would like to remind everybody, and all the messages will be recorded. So if you have any questions, you can just ask the previous speaker. Okay, Amir, go ahead.
Okay, thank you. Can you see my screen, presentation screen?
Yes, looks good.
Okay. Today I will present my preliminary results of my study. My title is The Impacts of Mediterranean SST Nudging on Performance of Community Hour System Model in Representing the Euro-Mediterranean Climate. I'm doing my PhD in Istanbul Technical University. As you know, the Mediterranean Sea Basin is important from the perspective of climate and population. So we focused on in this region. In climate studies, one of the widely used methods is utilizing ESMs. SST is one of the problematic parameters for ESMs. Biases of SST affect air-sea interaction in the model. We are motivated to utilize CSM and use the nudging method to make a better representation of the Mediterranean climate. So our purposes are applying SST nudging for only Mediterranean Sea and creating ensemble using this Mediterranean pacemaker experiment. Then we aim to investigate the role of Mediterranean Sea on the basin climate in detail. First, we obtained long-term simulations with pre-industrial conditions and anthropogenic anthropogenic conditions separately. We prepared observation data and customized the namelist file for the nudging method. To obtain ensemble simulation, we applied microperturbation in the atmospheric component, and we used nudging method on the ocean component with the Mediterranean mask file and observation data. In the figure located left-hand side, gray line shows the daily mean of Mediterranean Sea SST of control simulation. The blue line shows observation, and red line shows our Mediterranean experiment, which we use nudging method for Mediterranean SST. After nudging, results get closer to the SST observation as we expected. We hope that make the simulation results get better for also other parameters. We just compared temperature and precipitation with observation and 3 upper layer parameters with reanalysis data. We used a simple index to evaluate the Mediterranean experiment. The index basically uses differences between the control simulation and the Mediterranean experiment with observation. If the index is higher than 1, then it means the Mediterranean experiment reproduced parameter better over that region. First, we run the model for 200 years under pre-industrial conditions. Then we continue with anthropogenic conditions until 2014. Also, we used ERSST and OISST observation data to generate nudging simulations. Similarly, we produced new simulations with microperturbation. Basically, we have 2 main experiments, control and Mediterranean simulation. Each ensemble has 9 members. These plots show global means of radiation, temperature, precipitation, and SST. The left column belongs to pre-industrial conditions, right column belongs to control and pacemaker simulation. Values, range, and trends in time series look consistent, so we can say that we have a stability and balance in the model. This map shows temperature mean of the control simulation for a 30-year period. Figure B shows differences between control and observation. Control reproduced warm bias except for Amazon Basin, Sahara region, and Greenland. Also, control reproduced cold bias for north side of the Europe and warm bias around the Mediterranean Sea. This map shows the differences between Mediterranean and control simulation. In general, higher values are reproduced by Mediterranean simulation over the northern hemisphere. This is the index map. Green and blue colors show a better representation of the temperature reproduced by Mediterranean simulation. Accordingly, we have some improvements around the Mediterranean Sea and over northern Europe. The meaning of these maps is similar to previous one. In figure B, the bias of precipitation amount is higher over the equatorial region. Control simulation overestimates the precipitation over Europe in general. Dotted region on the index map show regions where correlation is insignificant. Mediterranean simulation has better representation over the entrance of Gibraltar Strait, Turkey, Balkans, and northeast part of Europe. These maps were plotted for 850 millibar temperature. In figure B, contour simulation has cold bias in North Africa and Europe. When we look at the index map, the Mediterranean simulation has a better representation of temperature over the north part of Europe along the upper latitudes. This slide represents 500 millibar geopotential high. In general, control simulation has lower values over latitudes near the poles compared with observation. According to bias map, the Mediterranean has some improvements over the north part of North America, Northern Europe, and over the mid-latitudes in the Northern Hemisphere. This is the wind. Wind is one of the tough parameters to simulate. When we look at the biases of figure B, we can see latitudinal patterns. The index map is not that clear, but Asia, east part of Africa, and the Indian Ocean have some improvements. For now, as I said, we have only preliminary results. We are trying to obtain better simulation for Mediterranean basin. Accordingly, the Mediterranean experiment has some improvements, but also poor representation of temperature and precipitation over some regions. To understand well, we will continue to analyze the ensemble data in detail. We will compare various parameters with the other observations and reanalysis data. As I said, we used monthly SST observation for this study. We might try the daily data for nudging method as further study. And we might think of member size of ensemble, and we can try other version of Ocean component of CSM. So thank you. Thank you for listening.
Thank you. Is there any question? Okay, Ella.
Did I understand correctly? You were nudging to time varying sea surface temperatures. So
Yes, exactly right.
okay, so do you see in like certain years maybe that there are big improvements? Is there much variability in the Mediterranean SSTs?
We use just Mediterranean CSST to create a pacemaker for Mediterranean. We used monthly data, and we will try to use daily data for Mediterranean SST as well. But yes, just for Mediterranean and sea surface temperature.
But it was a time varying and not a monthly climatology. Did I understand that correctly?
Oh, exactly.
So,
yeah. Not climatological. We use step by step in each calculation in the ocean part of the model.
Okay, so yeah, did you look at like kind of from year to year? Were there certain years where this might make a big improvement, and as opposed to just the climatology?
We haven't checked for the for using. Did you mean we might use yearly SST data or just analyze data year by year?
Yeah, I guess I was just thinking maybe there are some very extreme years where putting in the SSTs maybe would reproduce some extremes or over the Mediterranean land regions.
Yes, exactly. Yeah, for now we use it step by step when we nudge the model, and in the results we use 30 years time period. But when we look at the seasonal and day or year by year, probably it will change the effect. Yeah.
Okay. Thanks.
Yeah, thank you.
Any other question? No? Okay, thank you. Now let's move on to the next talk. It will be given by Qin Xue on the two-way coupling in a decadal North Atlantic SIT variability.
Yeah, thanks. Can you see my screen?
Yes, looks fine.
Okay, thanks. Great. Hi, everyone. My name is Qin Xue Sharon Gu. I'm a PhD student from Penn State University. Today, I would like to talk about the study done by me and my advisor, Dr. Mosi Gervais, on diagnosing two-way coupling in decadal North Atlantic sea surface temperature variability using time-evolving self-organizing maps. And the study has just been published in JRL. So the goal of the study is to understand the internal decadal variability in the North Atlantic sea surface temperature, or NASST, and the mechanisms responsible. So in order to focus on the internal variability, we use the CESM1 pre-industrial control simulation, and the model is fully coupled with the resolution of a nominal 1 degree, and the data is about 1,500 years long. So as I have mentioned in the title page, we are using a method called self-organizing map. So what is self-organizing map, or SOM? So SOM is an unsupervised machine learning method that can be used to classify high-dimensional data sets. Compared to some conventional methods such as EOF, it is not restricted by osmolality or stationarity, and therefore it can identify physical or relevant patterns. So for a conceptualized understanding, SOM is trained by constantly seeing the data, which is shown in this purple data cloud here. So during the training process, the generalized SOM pattern, which is shown in the black cells here, will get pulled towards the data cloud. And after the training, it can span the data space and represent the variability in data. So SOMs are often trained by input data vectors that contain a spatial pattern for a single time step. And we call this as an ordinary SOM. So you can understand the ordinary SOM as classifying pictures. However, the ordinary SOM is limited in terms of its ability to capture the spatial temporal evolutions. So for example, here is a picture of a kitty staying aloft. But by only looking at this picture, you are not able to understand or know what happens before and after this jump. Therefore, we developed this new evolution SOM method, or time-evolving self-organizing map method, based on the ordinary SOM. So for an evolution sum, an input data vector is a number of consecutive spatial patterns. So basically, we're classifying videos. So by looking at the same kitty example here, if that is a video here, you are able to understand why does this kitty jump and what happens afterwards, right? So this is an advantage of the evolution sum that is able to characterize variability in space and time simultaneously. So in our study, we applied this method to classify the spatial temporal evolutions of winter North Atlantic SST anomalies over the course of 10 consecutive years. In this way, we are able to identify evolutions without time filtering. Therefore, we can capture both interannual and decadal variability, and this would be more similar to what would be produced in a decadal prediction. Then let's look at some results. So these are the 24 generalized 10-year evolutions we classified from the North Atlantic SST anomalies in the CESM1 PI control simulation. So these results highlight the diversity of the SST variability in the North Atlantic. And in our follow-on study, we are exploring these different modes of variability. But in today's talk, I will focus specifically on this one node 1.6. So this node characterizes a 10-year evolution from a positive North Atlantic oscillation or NAO-like SST pattern to a positive AME-like or Atlantic multi-decadal variability-like SST pattern to a weak negative NAO-like SST pattern over 10 years, as you can see in the years 2, 4, 6, and 8, and 10 here. So focusing on this specific node allows us to demonstrate how the evolution sum method can provide new insights into this, into the mechanisms involved in this well-known NAO-AMB transition. And with this evolution sum method, we identify spatial patterns that cannot be well captured by the AMB index as shown in the top here. And we're able to capture the NAO to AME transition without using any time filtering. And we found this evolution occurs within 6 years. So in the paper, we talked about 3 dominant mechanisms, including the buoyancy-driven ocean circulation, wind-driven circulation, as well as the chain eddy forcing. So in this presentation, due to time limits, I will just focus on the chain eddy forcing mechanism because this localized chain eddy forcing might be hard to capture in some other frameworks. But in our study, thanks to this evolution sum method, we're able to capture this nuanced SST patterns over time, as I just showed in the previous slide. And therefore, we are able to identify the associated chain eddy forcing here. So in order to understand the coupled relationship, we use this diagnostic method proposed by Hosking et al. Called E-vector. So the E-vector can be used to describe vertical eddy activity propagation and its feedback onto the mean flow. And there are 2 components associated with the E-vector. The vertical component is the mean V prime T prime at 850 hectopascal, and it is the lower troposphere eddy heat transport. And it is a measure of the vertical eddy activity propagation. And the horizontal component of E-vector is shown in this math expression at 200 hectopascal, and it is an estimate of the eddy momentum forcing of the zonal time mean flow. So in order to isolate the baroclinic eddy activity, we use a high-pass filtering to the wind and temperature fields. Then let's look at the some composite analysis. So this is the sea level pressure and surface wind composite onto the year 2 of this node 1.6. So as you can see, the dipole in the sea level pressure field, which is the shading here, indicates a strong positive NAO-like signal. And consistent with this sea level pressure field, the composite of the SST, as shown in the shading here, also shows a very strong positive NAO-like signal with the enlarged SST gradient between the colder than normal SST in the subpolar North Atlantic and warmer than normal subtropical North Atlantic. And the on-field contours here shows the mean V prime T prime at 850 hectopascal. And as you can see, due to the surface baroclinicity associated with this large SST gradient, there is enhanced and upward propagated eddy activity. So this low-level eddy activity will lead to some change in the upper troposphere, as shown in this figure. So this figure shows the composites of the horizontal E-vector anomalies at 200 hectopascal in vectors, and the E-vector divergence anomalies in shading. So as you can see, associated with the lower level eddy activity, there is anomalous divergence of the horizontal E-vector anomalies components in the upper troposphere, as shown in the warm shadings in this region marked by this green box. So this implies that the enhanced eddy activity is providing energy to the mean flow in the upper troposphere. So this energy provided by the eddy will lead to an acceleration of the jet. So as you can see in the third figure, where the shading is the composite of the wind speed anomalies at 200 hectopascal, there is a port shifted and eastward extended jet as shown in the red shading compared to the climatology as shown in the purple contours here. And the location of the positive anomalies of the jet corresponds well with the E-vector divergence region here. So this jet response, as shown in this schematic in the black ellipse here, would force an equivalent barotropic geopotential height response, as shown in the low and high here. And this will lead to a dipole signal that is similar to a weak positive NAO. And this signal will act to strengthen the original positive NAO pattern and form a positive feedback. In addition to the year 2 condition as shown here, this coupled relationship between SST, chain eddy activities, and jet streams exist over 10 years. As you can see in years 2, 4, 6, and 10, the patterns of chain and eddy activities, as well as the atmospheric circulation anomalies, correspond well with the details in the SST anomalies over time. So I'm sorry that I didn't have time to touch all 3 mechanisms in details here because of the time limit, but please feel free to check this paper or reach out to me if you would like to learn more. And I'm currently visiting NCAR, so if you are in Boulder, I'm also very happy to talk in person. With that, I'm happy to take any questions. Thanks.
Thank you. It's very interesting.
Thanks.
Okay, any question? I have a quick question to ask you is you use this self-organizing map, you generate those number of nodes. And do you think all the nodes are independent from others?
They are like, in terms of the pattern itself, it's not really independent because self-organizing map captures a continuous change of the patterns. But in terms of the years associated with each pattern, each pattern, they're independent. So 1 year can only be, or 1 10-year period can only belong to one of the self-organizing map nodes. Does that make sense?
Yes. Yeah.
Okay,
thank you.
Thanks.
Steve.
Yeah, thanks for that talk. I'm wondering if the SOM nodes are multivariate nodes, or are they just based on SST?
They just based on SST.
So if they're not multivariate, then how do you do a composite? Can you clarify that?
Oh, sure. So let me show you a schematic here. Oh, wait a minute. So basically, so each of the input data vector will belong to one of the SOM node. So here, for example, I have a 4x6 SOM node here, and each of the input data vector will belong to one of the 24 nodes here. So for example, year 1 will belong to this node. And to do a composite analysis, we can just select these year numbers that belongs to one node and do the composite here. Does that make sense?
Yeah, and each input data vector then belongs to 1 year of a particular node.
Not 1 year. So each node has 10 year of the has a 10 year, and the input data vector actually all contains 10 years. So for example, the first input data vector is from year 1 to year 10, and the second is from year 2 to year 11. So each input data vector contains 10. So yeah, so when you do the composite, you are just like averaging over all the input data vectors that belong to this node, which all contain 10 years. Does that make sense?
Thank you.
Thanks.
Jerry.
Yeah, it was very interesting. I was just curious, out of all these nodes, how did you decide to pick node 1.6?
Oh, that's a good question. So actually in our follow-on study, we are actually looking at all the nodes, and they all have different behaviors. But in this particular study, we looked at this node because this node shows an NAO and me transition that is very well known, and we would like to kind of prove that our method is useful, and we can also provide some new insights in this. And focusing on one node allows us to use a large number of diagnostic variables. So that's the reason we choose this, but we are actually exploring the other nodes as well. Yeah.
Well, that node definitely has a nice progression of different patterns to different timescales. So that's a good choice. But yeah, that's interesting. Thanks.
Thanks.
Thank you. We'll move to the next talk. It's Hui. She's talking about the tropical cyclones.
Can you see my screen all right?
Yes, it's not in the full screen mode yet.
All right. Now?
Yeah.
Okay, thanks, Aisha. Hi, everyone. My name is Hui Li. I'm a project scientist in the CCR section here at CGD NCAR. So today I'm going to talk about the impact of tropical cyclone winds on Enso. This is in collaboration with Aisha Hu and Jerry Mill. So I believe everyone knows about Enso. It's the primary source for interannual variability over the tropical Pacific Ocean, and it has wide-ranging global impacts. And one aspect is that Enso can effectively modulate global tropical cyclone activity by altering the larger scale conditions. For example, during El Nino years, we typically have more TCs, tropical cyclones, in the Western Pacific and less TCs in the North Atlantic. But today's talk focuses on the reverse relationship or TC's impact on Enso. You may be wondering, why do we ask this question in the first place? It helps if we take a look at the Enso dynamics. So essentially, Enso is a neutrally stable natural mode of oscillation resulting from air-sea interactions. It is sustained by stochastic atmospheric forcing. And Enso characteristics depend on three important factors: the ocean state, the westerly wind bursts, as well as the ocean atmosphere processes, including the Kelvin wave propagation and warm pool expansion. And interestingly, tropical cyclones can influence all of these three critical factors. Let me elaborate on each of them. So for the initial ocean state, recent studies have found that tropical cyclones can actually increase the tropical Pacific Ocean heat content through their interactions with the upper ocean. Specifically, TCs can cause intense vertical mixing that eventually pump heat into the ocean thermocline. For example, in this experiment, we add transient tropical cyclone winds in the global ocean model and found that the added TCs can cause a anomalous warming in the equatorial thermocline, especially in the Eastern Pacific. And this kind of pattern is conducive to El Nino development. And the second factor is the westerly wind bursts. And recent studies have found that the majority of the near equator TCs are associated with the westerly wind burst events. So this provides another important ingredient for El Nino characteristics. And thirdly, the ocean equatorial Kelvin wave propagation that can help deepen the thermocline depth. So in this animation, I'm showing the ocean temperature anomalies in response to tropical cyclone forcing. These moving black dots are the tropical cyclone locations, and blue and yellow are temperature anomalies. So we can see some near equator TCs in this model can generate eastward propagating Kelvin waves, and carrying with them are the tropical cyclone-induced thermocline heating. So far, we see that tropical cyclones can influence all of these three important factors for Enso characteristics. So naturally, our question is to explore, our goal is to explore the impact of tropical cyclone winds on Enso characteristics, and in the context of a fully coupled Earth system model. So with that in mind, we are going to use an experiment where we add transient TC wind forcing into the fully coupled CESM 1.3. We're going to utilize two configurations of the CESM model. The first one is a high resolution. It has a 1/4 degree atmosphere. This simulation is mainly used to provide TC wind forcing. So at this resolution, the model can generate their own tropical cyclones with climatology generally consistent with the observations. So our first step is to find and detect all these TCs in the model. And for each TC day, we would take a snapshot of the TC surface wind within a 20-degree domain box. And then we archive the surface winds into a TC wind forcing inventory. And then we start running this low resolution fully coupled model. This model has a 1 degree atmosphere, which does not resolve TC strength winds, at least very little. So we're gonna add these TC snapshots into the low res model as the model integrates so that we can come up with this low res TC simulation where the TC's impact is embedded in this fully coupled model. So the difference between the low res control and the low res TC is just gonna be the added transient surface TC winds, and we can diagnose the impact of TC wind forcing within this coupled climate system by comparing these two simulations. So it turns out the TCs have a wide-ranging impacts on the global climate in this simulation. One of the most interesting aspects is its impact on Enso. So here we're looking at the time series of the Nino index of this 100 simulation. Left is in the control and the right is in the TC run. So just by eyeballing, we can see that the TC run has more strong to extreme El Nino events. And then we look at the monthly standard deviation of the Nino index. This black curve shows what it looks like in the observations, and the blue is from the control and the red is from the TC run. So we see that after you add in these transient winds, your Nino standard deviation has increased, but the shape of your annual cycle in the TC run is actually more consistent with the observations compared to the control. And then on the bottom right, we're looking at the power spectra of the Nino index. Again, the black shows what it looks like in the observations. So we see that observation has a maximum of a 5-year Enso period, and maybe a secondary peak at 4-year. But the control simulation showing blue here has one strong peak that happens at 4-year. And after we add in TCs in this red curve, we see that the Enso frequency, the Enso power generally has increased. And then the shape of the frequency distribution actually is more consistent with the observations with the 5-year primary period and the second period of 4 years. So we find that if you add in TC winds, you kind of shift the Enso frequency and the standard deviation annual cycle more approaching the observations. And then we're going to look at each of the El Nino events simulated in the model and focusing on the strong to extreme El Nino events. So this figure on the left shows the zonal SST distribution, equatorial SST distribution of every El Nino events. The blue shows in the control, and the red curves shows the events in the TC simulation. So immediately we can see that the TC simulation has a lot more strong El Nino events with warmer SST in the central to eastern Pacific. And in fact, there are 18 El Nino events in the control simulation, and 2 of them are El Nino extremes. And there are 19 El Nino events in the TC run, and 6 of them are El Nino extremes. It's just quite an increase. And on the right figure, we're looking at a linear regression between the Nino 3.4 index of the strong El Nino versus the near equator integrated TC wind power. So we can see, we find this very strong positive relationship between TC winds and El Nino strength. And especially there's a very strong event. It's this guy right here. It's also associated with the largest TC wind forcing. And then to better understand what's going on, we're going to look at the composite analysis of the El Nino. So here in the top figures are the composite El Nino SST. The left is control, the middle is the TC, and the difference are shown in the rightmost column. So we can see that the TC run has a warmer El Nino SST, especially during the peak, as well as when the El Nino is coming to an end, which is quite interesting. And the bottom shows the composite thermocline depth, equatorial, Pacific thermocline depth anomalies. Again, this one shows the differences. We can see that there is a deeper thermocline in the early season in the Western Pacific, and it kind of propagates eastward as the El Nino develops. And there is a strong, deeper thermocline at the time when El Nino is developing, and also at the time when El Nino is going to an end. I need to mention that this black contours on top of the colors are the composite tropical cyclone wind forcing. So we see that this deeper thermocline largely overlap with the enhanced TC winds. Additionally, we also look at the zonal equatorial current anomalies, and we see that there is enhanced zonal current in the TC simulation, which is also conducive to El Nino development. So put all of this into perspective, we're going to take a look at the El Nino dynamics. Specifically, we're going to look at the heat budget of the ocean mixed layer in the equatorial Pacific. So the heat budget, the two dominant terms of the heat budget is the thermocline feedback term as well as the advection feedback term. So we're going to look at the composite of these two runs in terms of these two terms. So the top shows the thermocline feedback term. So we can see that the TC wind, the TC simulation has a stronger thermocline feedback, especially in the Eastern Pacific. Actually, this pattern is quite consistent with the thermocline depth anomaly we saw in the last slide. And during the peak season, the increase of the thermocline feedback is about 20% compared to the control, 20% more. And then the bottom shows the advection feedback, zonal advection feedback. We see this pattern is actually very consistent with the increase of zonal current we saw in the last slide. And the magnitude is comparable with the thermocline feedback. So from this dynamic analysis, we found that TCs can impact El Nino through enhanced thermocline feedback and zonal advection feedback in the heat budget terms. So yeah, this is the summary of what I just said. So we are interested in the impact of TC winds on Enso. So we designed this experiment where we can prescribe high resolution TC winds into a low resolution fully coupled CESM. And then we find that added TC winds can increase the Enso power and shift the Enso frequency more approaching the observations. And we found that there's more strong to extreme El Nino events when we add in the TCs, and there's a positive correlation between strong El Nino and TC wind power. And we also found that the reason why TCs can impact Enso is through the enhanced zonal advection feedback and thermocline feedback. So our results indicate that these TCs can actively influence Enso in a fully coupled comprehensive Earth system model, pointing to an important two-way interactions between transient TC events and Enso. That's all I have. Thank you.
Thank you, Hui. Very nice talk. Now we can have some questions. Sarah?
Hi, thanks for your presentation. I was curious if you've looked at how the spectra of the zonal winds changed over the equatorial Pacific when you include the TC winds, particularly because I think it'd be interesting because a lot of models don't get the statistics of wind bursts correctly. And I'm wondering if by adding in the TC winds, you get a little bit closer to observations.
Oh, that's a great question. I haven't looked at the wind spectrum, but you have a great point. I think TCs may affect the westerly wind bursts in the model.
Thanks.
Take a note of that.
Brian.
Clarification about how you add the winds in. Does the atmosphere also feel the winds, or is it only the ocean that feels the wind perturbation?
That's another great question. So it's only the ocean because we actually add the TC surface wind stress into the model's coupler. So great. Yes, you know what I mean.
Yep, thank you.
Tony.
Yeah, I was just wondering if you thought about stratifying it in terms Central Pacific and Eastern Pacific Ensos, because what we've seen is in the 2000s a propensity toward more Central Pacific Ensos. Do you see the difference in TCs as a result?
Yeah, I did look into that. So the percentage of Central versus Eastern Pacificans are quite similar between the control and the TC. So the Enso type didn't change that much.
Right. Little bit of a surprise.
Yeah, I would say so.
Okay, thank you, Hui.
Yeah. Oh, actually.
If there's no further question, we move on to the update of CVC-WT working group. And Isla will give the update.
Okay, I'm gonna, because there was an update on Monday, I'll just do a very quick version of the update.
Wait, you can share your screen.
Sorry about that. My computer is frozen.
Oh.
Oh, this is not good. Oh, okay. Sorry about that.
Okay.
No problem.
So yeah, this is going to be a very quick, just in case anyone wasn't there on Monday. I'll just give a summary of kind of basically the new simulations that are about to be available or have just become available, and the new simulations that we'll be doing in the next few months. So I only want to spend a few minutes here because I think the important thing is to have the discussion. So one of the new simulations that is available, the website's not quite up yet, but it will be soon, are these pre-industrial controls with the new vertical grid of Cam. So on the left in the colors there, you see the new vertical grids that Cam will be using in the next generation. And you can compare that with the gray and the black, which is the old vertical grids. And so the grid spacing is on the x-axis and the height in the model is on the y-axis. And so basically the red one here is kind of the workhorse one, and it has a higher top than Cam, and it has higher vertical resolution, a grid spacing of about 500 meters in the free troposphere and lower stratosphere. And so we've run two pre-industrial controls that are kind of with the next grid, except the boundary layer additions that are circled here. So that Cam is going to have enhanced resolution in the boundary layer in the future, and we haven't changed that because when you do that, you need to worry about tuning the physics. So there are two pre-industrial controls of 100 years length with this, this new vertical grid, and this has a representation of the QBO. It has a higher model top, so hopefully an improved representation of stratospheric variability. And so these are unsupported and undocumented at the moment. So use these with care. They are available on Cheyenne, and we hope to document them at some point in the near future. We're also probably going to run some Amip simulations and a historical simulation with this grid too in the near future. Single forcing large ensemble is coming extremely soon. I had hoped to get the description paper done before this meeting, but I have failed to do that. So I apologize. It will hopefully be released in July. So this is complementary to the second 50 members of the CSM2 large ensemble, with forcings held fixed at 1850s, except those of interest. And there's going to be 4 sub-ensembles with greenhouse gas forcing in one, anthropogenic aerosols in one, biomass burning aerosols in one, and then everything else other than those 3 forcings are in the 4th ensemble. And I won't go through this, but this is a kind of global mean temperature response in the single forcing large ensemble. And I should mention that Nan Rosenblum did the work towards producing this. Okay, so the new simulations that we're going to do in the remainder of this allocation, we're going to do a regionally refined 1/8 degree North Atlantic Amip simulation using this grid that was developed by Rob England-Wills and Adam Harrington. This is going to run from the 1950s to present day with prescribed daily sea surface temperatures and sea ice taken from a 1/10 degree simulation. And the primary science goals here are really to see how ocean atmosphere coupling and North Atlantic jet stream variability change when we go to this kind of somewhat unprecedented high resolution for this length of simulation. There's going to be a 1,000 year long pre-industrial control with this pencil model, which has got kind of single column ocean models at each grid point. So it's somewhere between the slab ocean and a full 3D ocean, and has the advances over the slab ocean that there'll be like prognostic mixed layer depth and things. And Sarah's also been working with her group on this mechanically decoupled CSM, which she'll give an update on probably at the winter meeting. And then the final big project with the remainder of the allocation is led by Judith Berner, and this is going to be a 1,000-year-long pre-industrial control with stochastic physics. And so I will not go into any more details there. I just wanted to give a summary in case people missed it on Monday of the things that are happening. But what we really want to do now is have the discussion. So we need to come up with our proposal for the simulations for the next 2 years of computing allocation, and we're going to go into breakout rooms to do this, I guess, unless anyone has any questions on what I just presented kind of rapidly there. So we don't have long. We're supposed to have a 10-minute break in 10 minutes time. So hopefully that's enough to brainstorm in the breakout rooms for the next 10 minutes about things you'd like to see the working group do. Elizabeth, are you there, or should
I'm here and I'm ready to open the rooms.
Okay, great. Yeah, so we're gonna have 3 rooms, one with each of the co-chairs in, and we, if you could try and disperse yourself randomly in a kind of equal way into these 3 rooms, that would be great. Okay, so I guess I'll go in room 1.
Okay, I'll go in 3.
Okay. Okay, that was a fast 10 minutes, but we'll put the Google Doc in the chat. So if you have any other ideas, we'll probably email around to the working group as well, as we're getting the proposal together over the next month or so. So yeah, keep thinking about the experiments that you'd like to see. Does anyone have anything they'd like to bring up at this point before we go to the break? Okay, I guess we'll take a 10-minute break then and see you at 2:30. So I guess Danielle is not doing her talk.
Correct.
Oh, I think you're mute. Or, oh no, you're not
You hear-
muted. I just don't have my headphones in. Sorry, what did you say?
You are correct. Madi Hassan is filling in for that.
Oh,
class.
okay.
So we've got
Perfect.
a last minute addition, which is great.
Okay, excellent.
All right, it looks like we're at 4:30. So just a quick reminder for the speakers. It's a 12-minute slot, but you'll have 10 minutes to give your presentation. If you're starting to go over, I'll give you a reminder around 8 minutes that you've got about 2 minutes to finish up. And if I mispronounce any of your names, please, when you begin your presentation, reintroduce yourself with the correct pronunciation so we can all learn how we should be saying it, because we want to make sure we say your names correctly. So our first speaker is Madi Hassan. He'll be filling in for Danielle, who couldn't make it. And he'll be talking about the projected future changes and the role of Ekman heat flux on SST variability. Thanks for filling in last minute, Madi.
Thank you. Let's see. I hope you can see my screen.
Yep, that looks good. Thanks.
All right. So thank you. I'm Madi Hassan, a PhD student at NC State University. I work in Dr. Larsen's group. So today I'll be talking on, as Sarah said, projected future changes in the role of Ekman heat flux on SST variability. I'll quickly start with a very brief description of a particular type of atmospheric circulation, which is a Hadley circulation. As you can see in the figure right, Hadley circulation, it is basically a thermally driven meridional circulation, and it transport energy and momentum towards the pole. And as you can see in the figure, the edges of Hadley cell is where the surface easterly changes to the westerlies. And there has been a prior research for showing that the climate change impact the Hadley circulation. In particular, there is a polar expansion of the Hadley boundary. And as you can see from the figure on the right from Gries and Davis paper, where the blue line is showing the Hadley boundary computed from the reanalysis products. This is from Southern Hemisphere over the historical period. Consequently, there is a polar displacement of the subtropical wind belt. As a result, this will impact the wind-driven mean ocean circulation. And there is a lot of literature that shows how the climate change and especially the Hadley expansion can impact the mean ocean circulation. For the sake of time, I cannot get into details of all of these, but I show some snapshot of few papers where people looking at the mean ocean circulation change due to the climate change or Hadley expansion, either in a regional or global perspective. However, it is less clear how the Hadley expansion changes the ocean variability. And this sets up the motivation of my research. And that is any change in the prevailing surface wind due to the Hadley expansion may have potential influence on the SST variability, because two of the important drivers of the SST variability that are turbulent ARC heat flux and heat flux due to the Ekman heat advection are related with the prevailing surface wind. Therefore, on a large scale, both of these fluxes are related through their mutual dependence on the wind. And we can see that relationship from this figure. And this is showing the spatial pattern of the anomalous turbulent heat flux and Ekman heat flux. Where you see the blue, this is where the anomaly fluxes are opposite sign, and so they are negatively correlated. Where you see the red, they have the similar sign of the anomalies, and they are positively correlated. So if we look at the subtropic, where there is a mean easterly wind. This is where the anomalous Ekman opposes the anomalous turbulent heat flux due to SST variability, whereas in mid-latitude, they reinforce the anomalous Ekman reinforces the anomalous turbulent heat flux due to SST variability. Now, if we approximate a boundary, which we named as the Ekman transition boundary, this is the latitudinal boundary where the role of Ekman changes to the turbulent flux and SST variability. So based on this, we make an hypothesis saying that in a future climate, the polar expansion of the Hadley cell and the associated changes in the prevailing wind will result in a polar shift of the Ekman transition boundary. And it will have an important implication towards the subtropical SST variability that we've just seen in the previous figure. And the objective of this research is to quantify and compare the anthropogenic trends in both the Hadley and Ekman transition boundary based on the reanalysis product and CESM couple model over the historical and future climate scenarios. I use 3 different reanalysis data sets that are ERA5, ENSO, NCAR, and JRA55, along with 8 CESM6 models that are listed here with their corresponding ensemble member for historical simulation and also the future climate simulation. For future climate, I use a scenario where there is the highest greenhouse gas emission rate. And the period is 1979 to 2014 for historical period and 2015 to 2100 for future run simulation. So how did we calculate the Hadley boundary? So we noticed that from subtropic to mid-latitude, the prevailing surface wind changed from easterly towards, to the westerly wind. And if we take a look at the simple schematic showing on the right, if we consider, if we consider the zonal wind stress, it changes sign from subtropic to mid-latitude. And we grab the zero crossing where it changes the sign. And this is basically the Hadley boundary. And similarly for the Ekman transition boundary, we look at the latitude of zero crossing where the zonal mean correlation between the fluxes changes sign from negative to positive. This is the plot showing the correlation between anomalous turbulent heat flux and anomalous Ekman heat flux, similar to what we've just seen. But this is a time versus latitude plot where the spatial pattern, this is a zonally average. So in the x-axis, we see the time, and y-axis, we see the latitude. So in the subtropic, we see that the fluxes are negatively correlated, and mid-latitude, they're positively correlated. And we see a consistency of this relationship throughout the historical period. And the black solid line here is the Ekman transition boundary, which is showing the where the Ekman changes its role. And the dotted line is showing the Hadley boundary. So over the time, they move in tandem. And this result is based from the ERA5 reanalysis data set. Now, if we combine result from reanalysis and all the CESM6 model that we consider, this is the results over the historical period. And this is the scatter plot showing the latitudinal change in the Hadley boundary in the x-axis and the change in the Ekman transition boundary in y-axis. So a positive value in northern hemisphere means a polar expansion. This is the quantile which shows the polar expansion of both boundaries. And the small circle are the results from each individual ensemble members, and the large closed circle are the ensemble mean results. The black triangle is the multimodal ensemble, and the black triangle is the reanalysis mean. So we see that the majority of the ensemble mean results are falling in this quantile, which is a polar expansion of both the Hadley and Ekman transition boundary. And the shading you see, like the oval shape, is the confidence ellipse calculated from the ensemble mean. We see that the reanalysis mean falling out of the confidence ellipse, but it is within the spread of the ensemble results. So that means, and we use 3 reanalyses over a relatively shorter period of time. So natural variability can dominate from the reanalysis result. Alternatively, the CMIP6 result shows the force response, and it's clustered around 0. So there is, we do not see any obvious force response. And similarly, if we look at the southern hemisphere, we see that the change in the boundary is larger than the northern part. And we sort of see a linear relationship between the Hadley boundary and Ekman transition boundary. For southern hemisphere, this is the quantile where both the boundaries show a poleward expansion. Now, if we look at the future simulation,
2 minutes.
Thank you. We quickly notice that the trend does emerge in northern hemisphere and both in the southern hemisphere. The expansion is more pronounced in the southern hemisphere, where the multimodal ensemble mean for both the Hadley boundary and Ekman transition boundary has a relatively 1.5, close to 1.5 degree expansion. And this dashed line is showing us the perfectly linear relationship, so that we can have some sort of idea how the Hadley boundary modulates the Ekman transition boundary. As conclusion, I make an overall general hypothesis showing that the Ekman transition boundary migrates with the Hadley boundary. And based on the reanalysis and the CMIP6 simulation results, we see that the Ekman transition boundary is generally modulated by the Hadley boundary, both over the historical and future climate simulation. And anthropogenic trend is small over the historical period. However, in future climate projection, the trend does emerge. And these are the exact number of the expansion coming from the future climate projection. And so it is critical for climate models to predict the migration of the Hadley boundary with a reasonable accuracy to simulate potential changes in the ocean variability in future climate. And also the next thing that I would like to look up is to analyze the temperature budget at this expanded latitude to see or to quantify the overall SST variability. Thank you very much.
Great, thanks, Madi. Do we have any questions? Yeah, Isla?
Yeah, I was just wondering about the links to the extratropical jet as well. Have you looked at the kind of control of that on the boundary?
Yeah, I haven't looked at it, but yeah, there'll be, yeah, I haven't.
Okay,
yeah.
Thanks.
All right, I think we will move on because we're still right on time. So next we have Kyle Hatham. The title of the talk is A Large Forcing Attributed to the Variability of Biomass Burning Emissions in CESM2.
Hey, thank you. Do you see my screen okay?
Yes, looks great.
Perfect. Okay. So in a moment, I will be talking about how consideration of the variability in biomass burning emissions can act as an important contribution to the total aerosol forcing. But first, I'd like to acknowledge my graduate advisor, Hansi Singh, as well as our collaborators, and in particular, Phil Rash, whose ideas really form the basis for this work, but also help from Patricia Durrett-Pintigny, as well as Haruki Hirasawa. I'd also like to acknowledge the Polar Climate Working Group for providing the computational resources to go about this project. So I'll start with a little bit of background motivation for our work. So a short while ago, and actually presented at last year's CSM workshop, Patricia Durrett-Pintigny and colleagues had noticed that within the CSM2 contributions to the CMIP6 historical simulations, that there was this rapid acceleration in Arctic sea ice loss near the end of the historical period. This was in contrast to the CSM1 contributions to CSM5, where the Arctic sea ice loss was much smoother. And what they were able to do was actually attribute this to the way that the biomass burning emissions were prescribed within CMIP6. So if we look at the emissions over time, what we can see is that at the end of the historical period, there is this large step change in the prescribed variability. And this is due to the use of satellite observations during this period. And what Patricia Durapictini and colleagues were able to show was that this rapid acceleration in Arctic sea ice loss was actually directly attributable to this step change towards a larger variability in the prescribed biomass burning emissions. And then in conjunction with this work, a study led by John Fasulo et al. This year was able to link this increase in biomass burning emissions variability with a cloud thinning effect, which was particularly strong in the Northern Hemisphere mid to high latitudes. And then alongside this was also an increase in the amount of shortwave radiation absorbed at the surface, as well as a surface warming effect. Then following this, we were able to use the CSM2 large ensemble to show that this increase in biomass burning emissions variability also amplified the hydrologic cycle. So in particular, we saw increases in evaporation, atmospheric water vapor, as well as precipitation, again, all concentrated in that Northern Hemisphere mid to high latitude region. And then to put some of these numbers into context, so this increase in precipitation that we see due solely to that increase in biomass burning emissions variability represents about 6% of the signal from the mid 20th to the end of 21st century. So from these past three studies, we can see that consideration of this variability of biomass burning emissions is quite important when it comes to properly representing our simulated climates. But a big question that still remains is how important is this to trying to quantify the aerosol forcing? So in order to tackle this, we designed and ran a set of idealized simulations. So we did these within CSM2 using 2000s climatology. We also fixed the sea surface temperatures and sea ice concentrations, allowing us to directly calculate the radiative forcing by removing the majority of climate feedbacks. So what I'm showing here is two of these simulations where first we ran a fixed emissions baseline where we held annual mean biomass burning emissions constant. And then we also ran a second simulation where we exposed the model to this high variability period from the Amip6 prescribed biomass burning emissions. So by looking at the difference between these two models, this allowed us to see the difference that this variability in the biomass burning emissions has on the overall radiative forcing. So when looking at the global mean, we can see that this tends to increase the radiative forcing by about order of 0.1 watt per meter squared in the annual mean. But we can see that this is largely driven by increases in this high impact region in the Northern Hemisphere mid to high latitudes. And when we look at the annual mean increase due again solely to that increase in biomass burning variability, we can see that this is actually as large as about order 1 watt per meter squared when averaging from 50 to 70 north. So we can see from these experiments that our consideration of the variability in these aerosol emissions are important when quantifying the aerosol forcing. However, a question that still remains is why exactly do we see these changes? Even though we have the same amount of emission integrated over time, why do we see differences with the radiative forcing? So to tackle this, we ran another set of experiments where we idealized this biomass burning emissions variability and essentially isolating a temporal variability component. So using these idealized variability scenarios, we're actually able to reproduce a lot of the same qualitative features that we saw in the fully coupled runs and within the CMIP6 forced emissions variability. So firstly, we see that cloud thinning effect shown here in reductions in the cloud droplet concentrations, as well as a reduction in clouds indicated here through the liquid water path. And then these act in conjunction together to increase the cloud radiative effect. So we see that these differences in clouds are really driving these increases in shortwave radiation that is able to reach the surface. We can then zoom in on these high impact regions and look at how they evolve over time. And when we do that, we can see that within these idealized variability simulations, that we essentially have two different regimes. One that is associated with the high emission years and another that's associated with the low emission years. And what clearly pops out from this is that we tend to have a bias towards these low emission years where the effect of lower emissions really has a higher impact to the time integrated effect in the high emission years, which really starts to indicate to us possible nonlinearities in these fields. So to better tackle this, what we did was reran our fixed baseline emissions at varying emissions levels. And this allowed us to see the smooth response of these cloud fields to varying aerosol concentrations in the atmosphere. What we find is a strong nonlinear response in both the cloud droplet number concentrations as well as the liquid water path. And this is in agreement with a previous understanding of how these cloud fields react to changing aerosol concentrations, and most famously noted by Karsla et al. In 2013. So what these nonlinearities in these cloud fields result in is actually a nonlinearity in the total forcing with varying aerosol concentrations. We can then look at those CMIP6 variability, in particular the individual years from those fixed SST runs, and see that we see that nonlinearity pop out within those runs as well. And we can see here that it's those high emission years that really have less unit impact, both in the cloud fields and radiatively, than the low emission years. We can then take this one step further and actually see this nonlinearity within the fully coupled CSM2 large ensemble, really circling back to explain why we were seeing these large differences between the high variability and low variability scenarios in previous studies.
1 minute.
So, thank you. Okay, so I'll finish off with a few takeaway points. So first, consideration of this variability in aerosol emissions can have a large impact to the overall aerosol forcing. Increases in this variability we find tends to reduce the total negative forcing. And that these differences in the forcing are due to nonlinear cloud aerosol responses. So thank you very much for your attention, and I'm happy to take any questions if I have any remaining time.
Thanks, Kyle. Any questions? Yeah, we have a question from Isla.
It was really interesting. Just to make sure I understood your conclusions, your Amip runs look very similar to the coupled runs. So are you suggesting that you don't need any kind of like rectification effect of the ocean to kind of produce the overall temperature trends? It's really just kind of the direct influence of the forcing from the atmosphere?
Yeah, that's what we believe. Okay. There is possible nonlinearities with both the land and ocean that could be amplifying this effect, but we do find that by far the strongest effect is directly in the atmosphere with that first indirect effect.
Okay. Thank you.
Right, question from Brian.
Hey, Kyle. I guess my question is whether you found any particularly sensitive cloud regimes, or if it's really just whatever kind of clouds are there happen to be sensitive to this variability in emissions?
That's an excellent question, and something that we haven't dug in too deeply yet. We do find fairly strong sensitivity in more pristine atmospheres. It doesn't really answer your cloud regime question, but we do see a higher sensitivity in more pristine atmospheres as that cloud sensitivity is stronger at lower concentrations. But that is an excellent question and something that we should look into. Thank you.
All right, thanks. I think we'll move on to our next speaker. All right, so our next speaker is Igusti Ayudia Valentina. And the title of the talk is, see here, Changes in the North American Temperature Extremes Associated with the Shift in the Northern Annular Mode.
Can you see my slide?
Yes, looks good.
Okay. So good afternoon. My name, it's kind of long, but you can call me Dia. And I'm from, I'll just change this point. I'm a PhD student from the Hong Kong University of Science and Technology, and I'm currently visiting University of Wisconsin-Madison, working with Professor Elizabeth Maroon. And I'm here to share my research on the changes in the North American temperature extremes associated with the shift in the Northern Annular Mode, or NAM. So primary influences on mid-latitude weather are well studied, that it's influenced from the changes in the storm track and jet streams. And if we trace back, some precursor also coming from the global climate changes and internal climate modes, which Northern Annular Mode is the primary mode over the Northern Hemisphere. And if you see this work from Thompson and Wall 2001, you clearly see that how NAM is related to the colder surface temperature over the Northern American continent and the high sea level pressure over the Pacific and Atlantic, while it's low sea level pressure over the Arctic region. So from this, we came up with our research question on how much is the Northern Annular Mode, or NAM, influences the winter Northern American extreme temperature in a warming climate. So we used 40 ensemble members of CESM1 large ensemble to analyze the mean pattern considering the internal climate variability over the Northern Hemisphere. So coming to the first result of this work, here we want to see how the ensemble mean of CESM1 large ensemble, showing the main dipole pattern of the NAM. So this is the positive NAM pattern that showing a high sea level pressure anomaly over the Atlantic and Pacific, while it's low over the Arctic region. And this is calculated from the monthly data. So from this, we calculate the daily index from the PC time series of the first EOF from the monthly data. And if it's exceed plus minus 1 standard deviation, then we determine it as a NAM positive or negative phase. So from the future RCP 8.5 scenario, it's clear that there is a change in Pacific and Atlantic center, but in the Pacific, it's stronger in the future, and there's a shift also while it's weakened over the Atlantic. And you can see even more clear here in this panel, see that the shading is difference between future and historical. So there is a polar shift also in the Pacific center of NAM if you refer to the contour line as the historical pattern. And this result is supported by 15 CMIP6 model mean, which also indicate a stronger and the polar shift of the NAM Pacific Center. So we also try to look at the changes in NAM teleconnection pattern in a warming climate using a daily extreme temperature. So from the minimum temperature in the GFM winter season. So to see NAM positive in historical main characteristic and the minimum temperature, we see here that this shading is the minimum temperature composite during NAM positive. So there's an anomalous swarm over the central Northern American continent where it's slightly colder over the western coast. And this contour line showing the NAM. In historical, it supports the stronger westerly. And from figure B here, the NAM negative composite showing that in historical run, there's an anomalous cold that we all focus on, of like NAM teleconnection pattern, how it changed the temperature over the Northern American continent. But there's a small change over the western coast. So to see how it better represent the NAM composite, we plot another plot here to find the difference between minimum temperature in NAM positive and NAM negative. So it's well represent the colder NAM positive in the western coast and colder central Northern American minimum temperature. And in the future, the spatial pattern of this minimum temperature in different NAM phase is similar with a different magnitude. So to compare more clearly, you can take a look at these two figures. This is the historical and future of the composite difference. So the colder extreme temperature in this western coast of Northern American continent is intensified in the future, while this colder NAM negative is weakened in the future. So you can see here that there are changes. This is the difference between future and historical. So this blue color here means there are changes in both region. Well, it's weakened in this weakened in the central Northern America, but it's intensified here in the western coast. And this is also similar in 1506 model mean analysis. So we can suggest that there is a temperature advection that's play a role in this colder western coast due to the polar shift of the Pacific Center. And to see, to support our result, we plot another standard deviation of minimum temperature from daily data, ensemble mean of CSM, CSM1 large ensemble. So in the historical, it's clear that the minimum temperature is very small over the mid-latitude in the Northern Hemisphere, but it's weakened in the future. It's even more clear here in the panel C that difference between these two periods is showing weakening of this minimum temperature in the winter. So it's possible that NAM is possibly contributed to such weakening. And trace back to another precursor of such change in the NAM teleconnection pattern, we take a look at the storm track changes in the historical and the future run. So this plot is an eddy kinetic energy composite during NAM positive and NAM negative. So the warm color here showing that eddy kinetic energy is stronger in NAM positive in the Pacific Center. So it's CSM1 ensemble member showing these two characteristics of the storm in the Northern Hemisphere. But in the future, from this panel B, so this is high pass 10-day high pass filter, and it is intensified in the future. And if we find a difference, it's clear that there is a polar shift of this Pacific storm track. Well, it is match the location of the change of the polar shift of the NAM showing by the contour line in this figure. So to summarize my talk, the 40 ensemble members mean of CSM1 large ensemble suggests that in terms of NAM change, it will be intensified, and there will be a poleward or northeastward shift in the NAM Pacific Center. And in terms of NAM teleconnection pattern, there will be less extreme temperature variability in the future, and this coincides with a weakening in winter anomalous cold over the central North America during NAM negative phase. And another one here related to NAM teleconnection pattern is the cold advection associated with the polar shift of the NAM Pacific Center. It's result in a colder winter over the West Coast or Western North American during NAM positive. It's also consistent with change in storm track that is intensified, and there is also a polar shift in the Pacific storm track during the NAM positive. So thank you, and if you have questions.
Hey, thanks. Yeah. I have a quick question. You showed the, can you hear me?
Yeah. Yes,
okay,
yes.
great.
Sorry.
Yeah. You showed that the NAM intensification, I think, changed some of the centers of action. Were you able to connect that to any changes in sea ice over the same time period?
Oh, I haven't taken a look at that. Yeah, I haven't taken a look at sea ice changes here regarding to the polar shift, but it's a nice question. I can, yeah, take a look at that for the future work. Definitely. Thank you.
Other questions?
I'm not sure if there's something in the chat. Sorry.
Great. If we don't have any other questions, we'll move on to the next speaker.
Oh.
Will it let you stop sharing the screen?
Yeah.
Is it frozen?
I think so. I clicked this. Oh, I don't know how to.
Oh, are you in the annotate feature and now you can't see your mouse?
Yeah, I can't see my mouse.
Yeah, I wonder if I
maybe
can.
if someone else tries sharing, then maybe you can overwrite.
Here, I can stop your sharing.
Thank you.
Okay, great. All right, so our next speaker, we have Xiaowei Li, and the title of the talk is Impacts of Arctic Sea Ice Loss on Global Ocean Circulations and Interbasin Ocean Heat Exchanges.
Good. Thank you. Can you see my slides?
I cannot.
Oh, okay. Oh, sorry. Let me share. Yeah, can you see my slide now?
Yes, looks good.
Okay, great. Thank you. Hi, everyone. This is Xiaowei Li. I'm a PhD student from UC Riverside. And today I'd like to talk about a topic in which I collaborate with my graduate advisor, the impact of Arctic sea ice loss on global ocean circulations and interbasin ocean heat exchanges. Yeah, on the left panel, there are two figures showing the sea ice extent in September 1979 and September 2019. Well, on the right is a time series of the average monthly Arctic sea ice extent. So we can find that from observations, it's evident that the Arctic sea ice has declined a lot in the past few decades, which is also it has been identified as an important forcing driving climate change in the past few decades. So here in this project, we are interested about the global effects of the Arctic sea ice loss, particularly the changes in ocean circulations and ocean heat redistribution. In this project, we adopted the fully coupled climate model CESM1, in particular to replicate the sea ice loss in the past few decades. Here, we reduce the albedo of sea ice. We have performed 2 ASEMBL members, and all the ASEMBL members lost for 200 years. We first compare the simulated Arctic sea ice in our experiment with the observations. The top 3 panels are showing the observed Arctic sea ice concentration in 1918 to 1989, 206 and 2015. While the panels here are showing the difference between the 2 periods here. On the bottom 3 panels are showing the simulated Arctic sea ice in our experiment. So here, if we compare panel C and panel F here, we can find that our experiment can well simulate the Arctic sea ice loss in the past few decades. So we should identify the robustness of the results from our experiment. Here we further analyze the response of the sea ice and the ocean circulations in our experiment. The bottom panel, the green line here, is showing the changes in Arctic sea ice area. So we can find that it provides a force response within the first 10 years, which shows a very strong decreasing trend in this period. However, the ocean circulations, for example, the Atlantic meridian overturning circulation, the AMO, it provides a slow response based on a multi-decadal time scale. It suggests very slight changes within the first 10 years. However, after that, the AMOC suggests a very strong weakening trend. The AMOC weakening lasts for about 100 years, and by the end of this experiment, the AMOC has been weakened by about 6 silver joules. And here, besides the ocean circulation in the Atlantic basin, we find that the Indonesian through flow, the ITF here, which connects the Indian Ocean and the Pacific Ocean at lower latitudes. It also suggests a weakening trend in response to Arctic sea ice loss. And the ITF begins the weakening after 20 years in this experiment. And by the end of this experiment, the ITF has been weakened by about 1.5 silver joule. And consistent with the time-dependent changes in the Arctic sea ice and the ocean circulations, here we find that the response of surface heat fluxes and the ocean heat content tendons also suggest different patterns based on different time scale. The panel A and the panel B here is showing the forced response within the first 10 years. So the panel A here, we can find that the surface heat flux suggests positive downward anomaly in the North Atlantic. So which means the heat is entering the ocean in this region. And the panel B here is showing the ocean vertical integrated ocean heat content tendons. So we can find the positive anomaly here. So which means most of the taking heat is locally stored in this region, contribute to the ocean heat content increasing in the forced response. However, for the slow response for the panel C and the panel D here, we find that even the positive anomaly is still there for the surface heat fluxes here. However, for the panel D, we find that changes in the ocean content tendons, it suggests a weaker warming or even cooling in this region. This region here, the panel E and the panel F here are showing the difference between the two, between the forced response and the slow response. So we can find that compared with the forced response, even more heat is entering the ocean in the slow response. However, the ocean heat content suggests a cooling trend compared with the forced response. So which means different mechanisms may at play for different for the forced response and the slow response. And here we first analyze changes in the first 10 years to understand the forced response. On the left panel here is the changes for the atmospheric temperature. So we find that the Arctic sea ice loss leads to strong warming in the lower troposphere in the northern hemisphere. And the changes in the atmospheric temperature, it can amplify the temperature contrast between the ocean and atmosphere. So it can enhance the turbulent heat forces, leading to more heat can be absorbed by the ocean in the North Atlantic region here. To better understand the changes in ocean heat in each ocean basin, here we adopt the heat budget analysis. We define the ocean heat storage in each ocean basin equals to the ocean heat uptake in this region minus the sum of the outgoing interbasin ocean heat exchange at each ocean basin boundary here. So this is the description. And here on the left is the analysis for the heat budget in the Atlantic basin. There are 4 lines here showing the ocean heat storage, the black curve, the ocean heat uptake, the red curve, and the ocean heat transport at the ocean boundaries here. The purple curve here shows the boundary between the Atlantic and Arctic Ocean, while the orange curve here shows the transport between the Atlantic and the Southern Ocean. So we find that for the forced response within the first 10 years, the Atlantic suggests a very strong positive anomaly for the ocean heat uptake in this region, in this period. However, for the forced response, since the ocean circulation suggests slight changes in this period, so we find that most of the taking heat is locally stored in the Atlantic basin, contributing to the increasing trend of the ocean heat storage. Corresponding to the Increasing trend for the ocean heat storage on the right panel is the long average of the temperature trend. We can find the very strong warming trend between 14 degree north to 60 degree north from the surface down to about 3,000 meters level, with an equator-ward warming time between the 2,000 and the 3,000 meters in this region. And here we further analyze the later 100 years in this experiment to understand the snow response. On the left panel here is the temperature contrast between the atmosphere and the surface temperature. So we can find that the temperature contrast is amplified in the snow response. It can contribute to the downward anomaly turbulent heat frost in the slow response. On the bottom panel here is the difference between the first response and the slow response. So we can find that compared with the first response, more heat can be absorbed by the ocean in the slow response. However, for the slow response, the ocean circulation suggests very strong changes in response to Arctic sea ice loss. So it can modify the ocean heat transport between different ocean basins. And here on the left panel here is showing the ocean heat transport anomaly between the Atlantic and the Southern Ocean. The gold curve here is due to the velocity anomaly. So we can find that it dominates the alarming ocean transport at the Atlantic and the Southern Ocean boundary, as well as the total changes there. Well, the negative number here is showing that the Atlantic is exporting heat to the Southern Ocean. So which means for the slow response, even more heat can be absorbed by the Atlantic Ocean. However, most of the taking heat is transported away to other ocean basins. For the slow response in the Pacific, we find that in response to Immoc weakening, anomalous ocean circulation is generated in the Indo-Pacific, prescribed as a northward wind flow near the surface, while the anomalous southward wind flow near the bottom. And associated with the anomalous ocean circulation in the Indo-Pacific basin, we find that about one third of the redistributed heat from the Atlantic is imported by the Indian Ocean. The top panel here, however, the ITF, which connects the Indian Ocean and the Pacific, also suggests a weakening trend in response to Arctic sea ice loss. So the bottom panel here showing the ocean heat transport due to the ITF. So we can find that the Indian Ocean is also exporting heat to the Pacific. So which means about one third of the heat imported by the Indian Ocean is further redistributed between the two basins associated the ITF weakening in the snow response. In the Southern Ocean, thank you. Yeah, in the Southern Ocean, we find that the Arctic sea ice loss it can contribute to a mini global warming, with warming peaking in the lower troposphere, peaking around 50 degrees south, and the temperature and the changes in atmospheric temperature, it can further weaken the equator-ward flank of the western winds in this region. And the changes in surface wind can further to modulate the wind-driven ocean circulation in the Southern Ocean, which is the alarming smoke here. Even partially compensated by the eddy-induced smoke, the alarming smoke, it can dominate the changes in the residual smoke. And at the boundary there, it leads to an anomalous southward flow at the boundary there. And associated with the anomalous mean flow there, we find that the Southern Ocean is importing heat from other ocean basins. And here combine the ocean transport between the Southern Ocean and Atlantic basin. The orange curve between the Southern Ocean and the Indo-Pacific, the green and the blue curve here, we find that about 2/3 of the heat redistributed from the Atlantic basin is imported by the Southern Ocean. Even part of the heat is further released back to the atmosphere in the form of negative ocean heat uptake. The Southern Ocean is still suggesting an increasing trend of the ocean heat storage. And here are some of conclusions. We find that the Arctic sea ice loss promote ocean heat uptake in the North Atlantic warming region. However, the changes for the ocean heat storage suggest different patterns based on different time scale for force response within the first 10 years. The ocean circulation suggests flat changes. Therefore, most of the taking heat is locally stored in the Atlantic basin. However, for slow response based on multi-decadal time scale with strong Amip weakening, most of the taking heat is redistributed away to other ocean basins. About 1/3 of the redistributed heat is imported by the Indo-Pacific, which is further redistributed between the two basins with the Indonesian through flow weakening. And about 2/3 of the redistributed heat is imported by the Southern Ocean, which is achieved by the anomalous wind-driven ocean circulation at the basin boundaries here. And all the results have been published on Climate Dynamics. Yeah, thank you. Yeah, I'd like to take any questions here.
Thanks, Xiaowei. If we have one quick question, otherwise we need to try to stay on time. All right, well, if you come up with a question as we move into the next presentation, feel free to send it in the chat to Xiaowei. We can address it. So our next presentation is from Jiarong Zhang, and the title of the talk is Impact of the Pacific Sector Sea Ice Loss on the Sudden Stratospheric Warming Characteristics.
Can you see my slide?
Yes.
Okay, good. Hello, everyone. My name is Jiarong Zhang. I'm a PhD student at Coastal Carolina University. Today, I will be talking about the impact of sea ice loss over the Bering Chunky Sea on the sudden stratospheric warming characteristics. In my presentation, the Bering Chunky Sea is called Pacific Sector. I want to start with a brief overview of the sea ice. Previous studies have suggested a possible linkage between Arctic sea ice loss in autumn and subsequent weakening of the polar vortex. Some studies have argued that sea ice loss has a strong impact for mid-latitude weather and climate. However, the role of sea ice loss is still under debate since the internal dynamical variability is high. The figure on the right shows September sea ice concentration trend from 1982 to 2017. The figure on the bottom is a time series of sea ice extent. The observed Arctic sea ice over Pacific sector in September shows a strong decline in recent decades. However, it has received much less attention compared with sea ice loss over the Bering Sea. The stratospheric response to sea ice loss is sensitive to sea ice loss location. Therefore, the impact of sea ice loss over the Pacific sector requires further investigation. Besides the sea ice loss location, this linkage could also be modulated by QBO phase. Therefore, in our study, we focus on easterly QBO and try to assess the impact of sea ice loss in autumn over the Pacific sector on the stratosphere, particularly for SSW event. The numerical experiments were performed using CESM-WACOM6. WACOM6 has improved stratospheric variability, including an internally generated QBO and realistic SSW climatology. To understand the impact of sea ice loss, we conducted a pair of one-year experiments named the control and the low. This experiment starts from 1858 June 1st, and each contains 75 ensemble members. The figure on the left shows sea ice concentration difference between control and the low. The regional sea ice loss is greatest in autumn. Since the QBO might modulate the stratospheric response to sea ice loss, during our one-year simulation, we have to ensure the QBO does not switch phase. Here we show the time series of zonal mean, zonal wind average over QBO region. It starts from 1858 June 1st. Each line represents one ensemble member. Control is showing gray line, low is showing red line. Overall, the easterly QBO is consistent and similar between control and low during the winter. In our experiments, the effect of Enso, 11-year solar cycle, and global warming are all excluded. Next, I will discuss our mean model results. Here is a scatter plot that summarizes SSW characteristics in control and low during easterly QBO. Each bubble represents one SSW event. Control is showing gray, low is showing red. Overall, there are 55 SSW events in control and 50 in low. The x-axis is 100 hectopascal vertical wave activities averaged in 5 days before the onset. The y-axis is SSW intensity, which is defined by 10 hectopascal wind reversal during the event. The bubble size indicates SSW duration. Due to upward wave propagation perturbs the polar vortex, a linear relationship exists between x and y. By comparing the green bubbles and the red bubbles, we notice that the x value, y value, and bubble size tend to be larger in red, meaning that the CIS loss over Pacific sector triggers stronger upward wave activities and lead to more persistent and intense SSW events. The changes of these characteristics are significant. To understand how CIS loss impact the upward wave activities, we focus on 10 days before the onset. We start from the temperature field. The field contours are the temperature difference between control and low. On the left, it's average at high latitude and showing longitude versus altitude cross-section. On the right, it's average over Pacific sector and showing latitude versus altitude cross-section. The surface warming induced by CIS loss extend to lower troposphere before the onset. Additionally, there is a cooling response at high latitude west of dateline, as well as at mid-latitude. The cooling response is due to the cold air advection. So the temperature response to CIS loss could change the zonal and meridional temperature gradient. From thermal wind relationship, a positive zonal temperature gradient is associated with meridional wind increasing with altitude. A positive meridional temperature gradient is associated with zonal wind decreasing with altitude. On the left, 60 knots degree meridional wind is shown as purple line contours. On the right, the zonal wind average over Pacific sector is showing green line contours. Associated with horizontal temperature gradient, there is a stronger southward motion over northeastern Eurasia and a stronger northward motion over dateline, as well as a stronger westward motion at high latitude. Next, we show the 850 hectopascal geopotential height before the onset in control, low, and their difference. In control, we notice that the anticyclonic anomalies are over Europe and significant cyclonic anomalies are over North Pacific as well as Canada. These patterns of height anomalies are precursors of SSW event. When CIS loss occurred, the cyclonic anomalies over North Pacific are significantly amplified. It can enhance the upward planetary wave propagation. The cyclonic circulation response over North Pacific also suggests a stronger southward motion over northeastern Eurasia and a stronger northward motion over Alaska, which is consistent with the meridional wind pattern we mentioned in the previous slide. To further understand how anomalous wind and temperature enhance the upward wave activities, we decompose the poleward eddy heat flux into its linear and nonlinear component. These figures are shown at 850 hectopascal. On the left, it is the total eddy heat flux. Control is showing line contours. The difference between low and control are showing field contours. In control, before the onset, upward wave activities are mainly dominant over Sea of Japan. There are some small patches over North Pacific as well as North America. When sea ice loss occurred, the upward wave activities over Sea of Japan are significantly enhanced. By decomposition, we notice that the enhancement of upward wave activities over Sea of Japan are mainly contributed by linear term VA-TC. By checking the VA and the TC structure, we found the increase in upward wave activities over Sea of Japan arise from the coupling between southward wind response and the cold air there.
2 minutes.
Okay. So here we show the latitude versus altitude cross-section of EP flux. All the variables are the difference between control and low average in 10 days before the onset. The line contours is the wind field. Field contours is the divergence. The vectors are the EP flux. The all wave numbers are shown on the left. Wave number 1 is in the middle. Wave number 2 is on the right. From the vectors, CS reduction enhances the upward planetary wave propagation. The stronger wave activities convergence in the stratosphere. It weakens the polar vortex and lead to more persistent and intense SSW event. By comparing wave number 1 and wave number 2 component, we notice that in the troposphere, the enhancement of upward wave activities are mainly from wave number 2 component. So in our study, we found the CS loss over Pacific sector could change the SSW characteristics significantly. A dynamical mechanisms are provided as following. The warming induced by CS loss extend into deep troposphere prior to SSW. Through the thermal wind, the zonal temperature gradient enhances meridional wind throughout the troposphere. The coupling of wind anomalies and the temperature increase the upward wave activities. The wave drag induced could increase SSW duration and intensity with impact on cold air outbreaks at the surface. To summarize our results, the CS loss over the Pacific sector increased the SSW duration and intensity during easterly QBO. So I think I will stop here for any questions. Thank you for your attention.
Great, thanks. Any questions from the audience? Yeah, question from Isla.
Yeah, I was just wondering, kind of based on your understanding of how this affects the waves, if you have the Pacific loss accompanied by the loss in all the other places, as like in the real world, do you think you would see the same thing? Like, would you expect to see this in coupled simulations forced by greenhouse gases, for example?
Yeah, I think, yeah, so I think in our simulation, we only focus on the sea ice loss and we try to exclude other factors. But yeah, I think other factor will have an impact on the result, maybe require further investigation.
Thanks.
All right, thanks. We'll move on to Matthew Jenkins. Matthew will be speaking about the impact of sea ice loss on Arctic climate feedbacks and the role for Arctic amplification in CESM1 and ERA 5.
Great. Can you hear me and see my screen?
Yep, everything looks good.
Great. Well, thank you everyone for coming out today. My name is Matt Jenkins and I'm a third-year PhD student at the University of Albany in New York. And today I'm going to discuss the impact of sea ice loss on Arctic climate feedbacks using model simulations and the ERA 5 reanalysis data set. So just a brief overview for realized in very early modeling studies with increased CO2. So we can see in this figure from Hansen et al. 1984 that in the cold season, the largest Arctic warming occurs, and there's about 8 to 12 degrees Celsius of warming in the cold season, but in the summertime, there's only about 1 to 3 degrees Celsius of warming. However, the causes of this Arctic amplification are still debated, though, in the literature. So some mechanisms that have been proposed previously to cause the Arctic amplification are sea ice loss, where in the summertime, reduction of sea ice enhances absorption of shortwave radiation at the surface, and then there's a subsequent release of upward long wave sensible and latent heat in the autumn and winter seasons. Thermal inversions and the positive latitude feedback, enhanced polar energy transport, enhanced downlying surface long wave radiation, maybe from increased water vapor or clouds, and other processes. However, the sea ice loss, though, largely explains the seasonal and spatial patterns of the Arctic warming and the amplification. So since this is a talk about climate feedbacks, I just want to give a brief overview of how climate feedbacks impact the Arctic region. So in this study from Pithan and Mortson, they used the Amip5 quadruple CO2 runs, and they computed the warming contributions of different feedbacks in the Arctic. So if a process induces greater warming in the Arctic region than in the tropics, then that process is said to contribute to Arctic amplification. So that's the region right above this dashed gray line. So for example, the surface albedo feedback contributes to greater warming in the Arctic than the tropics. So that's a process that contributes to the amplification. However, a process that induces greater warming in the lower latitudes is said to oppose Arctic amplification. So another example of this is the water vapor feedback, since its effect is stronger in the tropical regions than the Arctic. And even though it does cause a little bit of warming in the Arctic, since its effect is stronger in the lower latitudes, it's said to oppose the Arctic amplification. However, many studies have cited the lapse rate feedback as a key cause of the Arctic amplification, since it induces warming in the Arctic region and cooling in the tropics. So the lapse rate feedback was attributed to the high stability of the Arctic atmosphere, meaning that that an atmosphere with high stability confines any warming signals near the surface, and that prevents any vertical mixing within the upper troposphere. So any warming is effectively confined near the surface. And under a bottom heavy warming profile, this essentially decreases how efficiently the atmosphere can cool itself. However, the question we want to answer here is, what is the impact of sea ice loss on local Arctic climate feedbacks? And since we know that sea ice loss is very important for the Arctic amplification, but how does the sea ice forcing itself impact the local climate feedbacks in the Arctic region? So to answer this question, we used two CESM1 model experiments, which were used previously by the study et al. 2019. And our two runs, the first experiment is a standard 1% per year increase in CO2 run with fully coupled dynamic sea ice. And we also run a fixed sea ice run, which is the same as the 1% CO2 run. So the CO2 still increases by 1% each year, except the effects of the Arctic sea ice loss are excluded. And in the simulation, what et al. 2019 showed is that fixing the sea ice effectively cuts off the Arctic amplification. So the Arctic warms at a similar rate to the rest of the world in the fixed ice run. So each simulation is run for 235 years, and we look at the time period years 131 to 150 relative to the pre-industrial control climatology, where the CO2 is fixed at about 284 parts per million. So, and also we compute the feedbacks with the radiative kernel method as well. So here are some results where we're looking at the feedbacks by how they impact the TOA flux change. And first I want to draw your attention to the surface albedo feedback to the very left and the oceanic heat uptake to the very right. So as you can see by the red bar, which represents the summer surface albedo feedback in the standard 1% CO2 run, it's very large. And under the fixed ice case, the surface albedo feedback essentially gets cut off. And then in the winter season, which is indicated by in the winter season with the oceanic heat uptake, which is to the very far right of the graph, we can see that there's large oceanic heat release of energy to the atmosphere in the winter, which causes much of the bottom heavy warming. And we don't see this in the fixed ice case. So now moving on to a couple other results, looking at the Planck and lapse rate feedbacks in the wintertime, we can see in the gray bar in the standard run with the dynamic sea ice that the Planck feedback is largely negative, and the lapse rate feedback is very positive. But in the fixed ice case, which is represented by the green bars here, that both of these processes are greatly reduced without that oceanic heating and large surface warming caused by the sea ice loss. And lastly, we look at the atmospheric heat transport, as this has also been cited as a cause of Arctic amplification. We can see that with fully coupled dynamic sea ice and the large bottom heavy warming, that the atmospheric heat transport is actually equatorward. So this opposes the Arctic amplification, but in the fixed ice case, so the heat transport is anomalously poleward. So now looking at some spatial patterns for some of the feedbacks here are the spatial patterns of the laterite feedback, which is in the shading and the contours of the sea ice loss. And in this panel, we show the results from the 1% CO2 run during the wintertime. So we can see that over the areas with the largest sea ice loss, that the laterite feedback is enhanced over these areas. So right in where I've circled with the blue circles here, where there's about 40 to 80% sea ice loss, that's where the largest laterite feedback response occurs. And we don't see that necessarily in the central Arctic. However, in the fixed ice case, the winter laterite feedback is greatly reduced over most of the Arctic everywhere. So now we wanted to compare our model results from the ERA 5 to the ERA 5 data set. And to do this, we look at the years 1990 to 2019 relative to years 1950, 1979, and once again using the radiative kernel method. And here we want to emphasize what the spatial patterns of climate feedbacks are in the Arctic region. And just for the sake of time, I just focused on the laterite feedback, but our studies do look at the spatial patterns of the other feedbacks as well. But here is the relationship between the laterite feedback and the temperature inversion, which we used as an estimate for the stability of the atmosphere. So we estimate the temperature inversion as the temperature difference between at the temperature 850 hectopascals and 1000 hectopascals. And that's represented by the shading, where the red is more stable conditions and the blue are more unstable conditions. And the contours are the strength of the laterite feedback. So we can see that in the wintertime, that the strongest laterite feedback occurs in the Atlantic sector in the Arctic, where there's quite a gradient between the different stability regimes. And looking at the pattern correlation, which is 0.26 between these two fields, there's not a very strong relationship. We get a little more of a moderate relationship between the stability of the atmosphere and laterite feedback in autumn, but just looking at the figure qualitatively, the spatial patterns of both processes do not line up very well. But looking at a map of the laterite feedback and the sea ice loss, where the shading in this figure is the sea ice loss, the green contours are the surface warming, the red contours are the laterite feedback. We can see that where there's large sea ice loss along the Atlantic sector in the Arctic, that's where the largest surface warming and laterite feedback response occurs. And we also get a similar relationship in autumn. So we can see that there's more extensive sea ice loss in the Pacific sector in autumn. There's also large surface warming and laterite feedback as well in those regions. So just to briefly summarize here, the summer surface albedo feedback and winter oceanic heat release are reduced without sea ice loss. The winter laterite and plank feedbacks are reduced without the sea ice loss and the oceanic heat release during the winter time. And also we found that the winter laterite feedback closely follows the patterns of sea ice loss, where the surface warming is the largest, but not necessarily the mean temperature convergent conditions. And also we found that in the fully coupled case with large sea ice loss and surface warming, the net atmospheric energy transport is equatorward and not polarward. So this suggests that large AA causes an equatorward atmospheric energy transport. So here are the studies that we have. One of them is already published, the CESM1 simulations in GRL. The other one, we just got back for our revisions, and we're currently revising that paper. And in both studies, we discuss each feedback besides just the laterite feedback in greater detail. So I'll stop right there, and I'll be willing to take any questions that you may have.
Thanks, Matt. Any questions from the audience? Okay, there's a question in the chat. It says, I believe when you refer to sea ice loss, you mean sea ice concentration loss, not thickness. Is that correct?
Yeah, yes, the sea ice fraction. Yep, not the thickness. Yep. So that would be an interesting thing to look at in the future, though, too. The impact of the thickness.
All right, thanks. In the interest of time, we'll move on to Yuting Mu. And the title of this talk is Decomposing Projection Uncertainty for the Seasonal Evolution of Arctic Amplification.
Okay, thanks. Sorry. Can you see my screen?
Yes, your sound is a little echoey. But
it's so just wait for a minute. Okay.
Yeah, if you're also on the YouTube channel, exit out of that. That sometimes helps.
Is that better, or?
I think it's good enough to keep going, so we don't get too
Okay,
far
okay,
off.
okay, sure. Okay. So hi everyone. Today we're talking about the seasonal evolution of Arctic amplification. We also analyze its decomposed uncertainty in projection. I'm Yuting Wu from National Taiwan University, and my advisor is Yuchao Liang. And also thanks for all these people to improve these studies. Okay, so let's get started. So Arctic amplification factor, which means the Arctic once more the rest of the globe, is a robust phenomenon in model simulation or in observation. And many studies are examining AA and its possible mechanism in annual mean. But recent studies are also discussing about the seasonality, like the left panels. Hanado find out the seasonal asymmetry of Arctic warming, which Arctic warms more in winter than in summer. And it also indicate that this is driven by the sea ice effective heat capacity. And the right figure shows that Leonardo used larger ensemble and find out a seasonal shifting of maximum Arctic warming from the autumn to the winter, and so as the Arctic amplification factor. However, this results also shows a large model-to-model difference. The uncertainty analysis of Arctic amplification is in seasonality is still unclear. Okay, so following these questions, here is my scientific questions. First, how do Arctic amplification involve in seasonality, and what mechanism drives the seasonal evolution of Arctic amplification? And the third one is how do uncertainty looks like in these signals? So from the question 1 and 2, I use the 6 single model initial condition large ensemble, which is under RCP 8.5 scenarios. We analyze the Arctic surface air temperature, precipitation, sea ice area, terrain heat flux, and also the Arctic amplification factor. Also, we use the simplified simulations data with different RCP scenarios. Okay, and about the questions, the third question, we use the uncertainty decomposition analysis following Learning et al. And Bonin et al., which we decompose the total uncertainty into 3 main sources, which is model structure uncertainty, scenario uncertainty, and internal variability uncertainty. And the model structure means the variance across the ensemble means of 6 miles. And the scenario uncertainty means the variance in the multi-model mean under 3 different RCP scenarios. And the general variability means the mean of the variance across the ensemble means in each miles. Okay, so in this analysis, we're focusing on the Arctic amplification factor, on Arctic temperature, precipitation, and also CS area. Okay, so so first, we're looking at the seasonal evolution in Arctic climate in large ensemble and find out its possible mechanism. So as you can see, here shows the 4 variables in seasonality. And in each column shows different models. And in each panel, the x-axis stands for the year, while the y-axis stands for the months. And the dot in the panel stands for the maxima within 12 years in each year. So first, we compare precipitation and temperature. We found that there shows the clear seasonal evolution, which is maximum value shifts from the October to the November or December. And these results are shown in most of the models. And next, we analyze the turbulent heat flux. And we also find out these similar signals, which the maximum turbulent heat flux also shifts from the autumn to the winter. And this signal is quite similar to the temperature, which means that there was a strong connection between temperature and turbulent heat flux. And next, we move on to the sea ice area, because we know that in under global warming, the more sea ice loss and the more open water heat release, and the more heat from the ocean to the atmosphere heat release, so as the turbulent heat flux. So as you can see, the sea ice area also shows the seasonal shifting, which is from about September to the October, to the November or December. But compared with turbulent heat flux, the shifting is about 1 month earlier than turbulent heat flux. Okay, so the primary mechanism is that the seasonal evolution of sea ice loss what drives the seasonal shifting of turbulent heat flux, which is in advance drives the Arctic temperature increase and precipitation increase. And another interesting thing is that compare model to model, there also shows the large model spread in all of these signals. Okay. And next, we move on to the Arctic Amplification factor, which is defined as the Arctic warming divided by the global warming. And in this panel, it also shows the clear seasonal evolution, which is maxima shifts from October to November. And it's quite similar to the Arctic warming. But the difference between the Arctic warming and the Arctic Amplification factor is that the Arctic warming will increase constantly as time progresses, while you can see that the Arctic Amplification factor will reach its maxima about 2050 and then decrease. Okay, so here's the difference. And however, we compare each panel, which also shows the large model spread in the AF. Okay, and in addition, we also test different scenarios. And so in this figure, shows the Arctic Amplification factor at the end of the 21st century. And in each panel, the y-axis shows the 18 models in CESM5, and the number in the brackets shows the shifting months of the maxima AF from RCP 2.6 to 8.5. So as you can see, the maxima AF in RCP 2.6 are located in November, while when we're looking at the RCP 8.5, the maxima AF will locate in about November to December, which means that they also exceed the scenario differences in the AF. And so following this question, we'll next move on to the next analysis, which we do the uncertainty decomposition analysis in large ensemble. Okay. So this figure shows the 4 variables we are focusing about, and we do the uncertainty decomposition. So the first column shows the total variance, which is the total uncertainty values in seasonality. And the other 3 columns is the corresponding uncertainty values. Okay, so first we're looking at the first column. It shows that these 4 variables shows the clear seasonal evolution, which is also shifts from the autumn to the winter. And compared with the model variance, it also shows the clear seasonal evolution, and this signal is quite similar. And we next compare with scenario and internal variability uncertainty. The scenario and the internal variability do not show clear seasonal evolution, and its value is quite smaller compared with model variance. Okay, so we can know that the model uncertainty will dominate the total uncertainty in this seasonal evolution. And another interesting is that when we focusing on the scenario variance in the AF, in which is panel K, it shows a similar increase of scenario uncertainty compared with other scenario uncertainty, which means that the model uncertainty will be more important in the AF, which also means that we have to be more cautious about the model spread in the AF when calculating in seasonality. Okay, so to conclude our study, first, we analyzed the seasonality of Arctic indication and precipitation, and we found out that the annual maxima of AA and its precipitation will shift from autumn to winter in the 21st century. And this is due to the sea ice loss and its corresponding turbulent heat flux. And next, we also do feedback analysis, which is not shown in these slides. But we find out that the lesser feedback and plant feedback is not the dominant terms in seasonality. Okay. And the second thing is that, and the third thing is that we do uncertainty decomposition analysis, and we find out that the model uncertainty will dominate the total uncertainty with respect to how months it shifts and in what year it shifts. And the next thing is that we found out the smaller scenario uncertainty of AF in seasonal evolution, and which is not like the Arctic warming and precipitation. So then we have to be more take care about calculating AF in seasonality. Okay, so that's it. And thanks for listening.
Great, thanks, Yuting. Looks like we have a question from Laura Landrum.
Hi, thanks, Yuting. Can you hear me?
Yeah, I can hear you.
Okay, great. Thanks for the talk. I just want to make a comment with this talk and the previous talk that you're once again you're looking at sea ice concentration losses, and that I think we should be careful when we're referring particularly to heat fluxes in the winter, whether the sea ice loss implies sea ice loss, which can also be a volumetric change and a thickness change versus a concentration change. And in the models that there will be a period of time in each of these models when the concentration losses are not great, but the thickness losses might be significant, and they can add a significant source of heat in the winter. It's that you're not going to see that so much in the summer, but in the winter. So for example, the CESM1 large ensemble, you'll see about a 10 watt average or so, 10 watt per meter, 10 to 12 watt per meter squared increase in surface in the conductive heat flux over sea ice covered areas just from the thinning of the sea ice from the beginning of the 20th century to about 2070. And so maybe something either to consider, or at least when we communicate, make sure that it's sea ice concentration versus sea ice thickness, because when you're looking at seasonality in the winter, the thickness can be an important factor.
Yeah, okay, I see. Okay, so I see. So you're talking about the sea ice concentration and thickness. I think
so once you start getting sea ice concentration losses, that change in the heat flux from the ocean to the atmosphere is going to be much larger than where, sea ice is just thinning. However, you will still get an amplification due to a thinning of the sea ice before the concentration loss, because the conductive heat flux depends on the thickness, right? And also snow makes a big difference. So it may be one thing that, in the smaller details in terms of the winter heat fluxes plays a role when you're looking at different models, like how fast are they losing volume of sea ice, not just concentration.
Yeah, I see. Okay. Thanks. I will look onto it.
Okay. Thanks.
Thanks.
Great, thanks for that question. And with that, we will move on to our last talk. All right, so we have Haruki Hirasawa, and the title of the talk is Estimating Effect of Ocean Circulation Changes and Historical Forcing Impact on Late 20th Century Monsoon Climate with the CESM1 Slab Ocean Model. I can see the screen, but I don't hear anything if you're talking.
Sorry, I forgot to unmute
Okay,
myself.
great.
Okay, great. Yeah, so thank you. Yeah, my name is Haruki, and today I'll be discussing some work that I've been doing with my supervisor at the University of Toronto, Paul Kushner. And what we've been doing is using CSM1 the large ensemble as well as slab ocean model simulations in order to try to estimate the effect of ocean circulation changes in the late 20th century. And so, yeah, it turned out to be more challenging than at least I expected. So hopefully you'll see that. Okay. Okay, so the work I'm doing here is building off of the CSM1 large ensemble single forcing simulations. So here I'm showing the land precipitation and sea surface temperature anomalies from the large ensemble for the all forcing on the left, the ALBA aerosol in the middle, and then the difference, which is the aerosol effect on the right, for 2 periods in the late 20th century. So on the top row, I have the 1970s minus 1950s, and then on the bottom, I have the 2000s minus 1970s. So these are the 2 periods I'll be using for the rest of the talk. And they're sort of chosen so that one captures a period where aerosol emissions are generally increasing, particularly over Europe and North America. And then the second period is sort of capturing the period where we're getting a west to east shift of emissions. And so if you look at the precipitation patterns here, you see that, not surprisingly, greenhouse gas forcing is increasing precipitation in the Asian and African monsoon regions. But actually in the historical period, at least, most of the historical forced rainfall variability is being caused by aerosol forcing, where it's drying in much of Asia and Africa during the aerosol increase period, and then during the aerosol shift period, you get continued drying in Asia and increases in precipitation in Africa and the Middle East. So what we want to do is try to understand the mechanisms that cause these precipitation changes. And so what our approach is to try to decompose the total coupled response into different timescales. And so this has been done by many people with using the ocean model hierarchy in order to separate out these different timescales. And so in particular, people have used fixed SST simulations wherein, if you just apply a forcing with fixed SSTs or without changing SSTs, you get this, what I'm calling direct atmospheric, but what's often called the fast effect, where it's just atmospheric radiation and circulation adjustments to the forcing, plus the effect of any land surface temperature changes. And so these typically occur on the day to month timescales. And then those are sort of separated from the slower ocean mediated processes that are the result of ocean surface temperature anomalies that then feed back onto the atmosphere. So this is often called the slow effect. And so I think fast and slow were used in a previous talk to refer to very different timescales. So here, which is why I'm trying to use these more precise terminology. And so in this paper, in this talk, I'm instead using slab ocean model simulations. And so the idea is that instead of separating out the direct atmospheric effect with these slab ocean model experiments, we can instead separate out the ocean circulation effect. Okay, so yeah, slab ocean models. So this is a type of model where the ocean is represented by a fixed single mixed layer, which has diagnostic temperatures, but all other ocean properties are fixed. And so processes like ocean circulation and heat exchanges, both laterally and vertically, are represented by what's called a Q-flux, which we can calculate using POP2 data for the CSM SOM. And so the experiments we've conducted here are what we do is we're trying to target the 50s, 70s, and 2000s for the all and ALBA aerosol forcing experiments. And so we use the large ensemble, coupled POP2 outputs to calculate the Q-flux fields, which we apply as boundary conditions to our simulations. And so here I'm showing sort of a schematic of the different experiments we've conducted, where on the x-axis we have the Q-flux, and on the y-axis we have this global mean surface temperature. And so just to take a look at the blue here, which is the ALBA aerosol forcing, which is a bit simpler. We can first change the Q-fluxes that we diagnose from the large ensemble. And so a positive Q-flux, these are positive down. So a positive Q-flux is causing a cooling corresponding to ocean heat uptake. And then we can then, while keeping Q-fluxes fixed, impose a forcing change increasing CO2, and this then warms up. And so the idea is that in principle, if we set everything up correctly, if you add up the effect of the Q-flux and the effect of the forcing, this should approximately equal the full ocean model response. And so with these simulations, we essentially get two methods for estimating the ocean circulation effect. The first is to take the difference between the full ocean model, the large ensemble, and the slab ocean model where we change forcings. And the other is to take a look at the effect of changing the Q-fluxes. And we're going to focus here on the residual method for reasons I will show you right now, which is that unfortunately, we couldn't get the Q-flux perturbations to give us reasonable results. So if we compare the full ocean model large ensemble surface temperature anomalies to the slab ocean model surface temperature anomalies, we see that there's reasonable agreement in some cases, but in particular, this ALBA aerosol 2000s minus 70s effect, for whatever reason, the Q-flux cooling effect is much too weak. So we get way more warming in the slab ocean model than in the full ocean model. So for the rest of the talk, I'll be focusing on the residual method. And if anyone has any questions about, or sorry, any suggestions on why this might be occurring, I definitely appreciate that. Right, so here I'm showing the results from the slab ocean model simulations. So for these figures, I'm showing the July, August, September surface temperature anomalies in the large ensemble on top, the slab ocean model where we keep Q-fluxes fixed and then increase the forcings in the middle. And then on the bottom, the difference between the two, which we're inferring to be the ocean circulation effect. And so, we see that in general, the ocean circulation is damping the transient warming signal corresponding to ocean heat uptake. And it's also redistributing heat away from the Arctic and North Atlantic, also damping a lot of this north-south interhemispheric gradient in the SSTs. And so this obviously has impact on the precipitation in the monsoon regions that that I sort of pointed out before. And so again, it's the full ocean model on the left, the slab ocean model in the middle, and then the inferred ocean circulation effect on the right. And so we can see that the ocean circulation effect is sort of counteracting, gradients in the Atlantic SST. And so this is, it's damping this first southward, then northward shift of the Atlantic ITZ in the two periods. We also see that it's counteracting a lot of the drying we see in Africa and East Asia, and it's also reducing precipitation in South Asia and the maritime continent. And so if we then remove the ALBA aerosol effect, we can take a look at the aerosol forcing effect. And so here, the effect of ocean circulation of reducing precipitation in Africa and Asia is much clearer. And interestingly, actually, even though we get a reduction in aerosol forcing over Africa and the North Atlantic in the later 2000s -70s period, we're still getting a positive rainfall influence of ocean circulation. So it seems like perhaps this, maybe, yeah. So I guess the ocean circulation effect might be reacting or like responding to decades old aerosol cooling forcing effect. Yeah. Okay. So just to conclude, so we've tried using these slab ocean models and diagnosing the Q fluxes from the large ensemble to set up these simulations such that we can reproduce the large ensemble anomalies with the slab oceans. But unfortunately, this didn't work for us. So we're instead relying on the more simple residual method. But we still see some interesting things where the ocean circulation sort of reduces hemispheric asymmetries and reduces transient SST signals. And in regions like, for example, the Sahel, the ocean circulation is as damping the effect of aerosol force drying and reducing that drought signal. Yeah, so thank you.
Thank you. Any questions from the audience? All right, it's probably the end of the session, so everyone's getting a little saturated. Let's see. Got the agenda here. So that wraps up our second session of talks. And let's see if the other co-chairs are here. Oh, there's Isla. So do you want to kick off the discussion?
Yeah, so I guess we have a 15 minutes or so left, or 20 minutes. So it'd be good to, continue discussing more of the proposed simulations, because we didn't have too much time in the breakout rooms. I guess we can just kind of go over what was suggested in our breakout rooms. So I can start with our one. So I think there were 3 main suggestions or topics. So with this allocation, Brian Medeiros has been working on this regionally refined tropics. So there might be more, he's just been kind of developing the configuration up to now. So there might be more things to do with that. It might be interesting to look at that in the context of the QBO-MJO connection now that we will have a QBO in the model. The other thing was building off of the regionally refined North Atlantic simulations, or simulation that we're about to begin, kind of depending on how that goes. We might want to have some control experiments and also some kind of perturbation experiments to explore any influences we find, like maybe smoothing the SST anomalies or SST itself, to kind of see what is the role of having that high resolution SST versus having the high resolution atmosphere. So there's probably things to think about there with building off of those experiments. Unfortunately, we don't have any results yet from that. It hasn't started, so we don't know like how fruitful it's going to be. But there could be things to do there. And then another suggestion from Hansi was maybe, when we keep having this issue with new model configurations with the Labrador Sea freezing, and maybe some perturbed parameter experiments to explore kind of what produce it, what is that sensitive to. And I don't have enough knowledge myself to know exactly how this would go and what we would perturb, but something to think about. So I think that's pretty much what we had in R1. If I've forgotten anything, other people can jump in. So yeah, Sarah, I don't know if you want to go through what was said in your group.
Sure. Yeah, we had, I guess I would categorize it kind of as 2 different main topics. One was about data availability, being able to access existing or soon to be publicly available data sets, and the other one was potential experiments. So I'll start with the former. So there was a little bit of concern about access to the CESM2 historical and future runs, I believe, on the climate data gateway, and that not all members were there. And so there were questions about how to get access to those runs if one doesn't have access to Casper. So that was the first thing.
Is that the CMIP runs or the large ensemble?
I think the CMIP runs.
Okay, I don't know. I feel like maybe some were withdrawn or something. I don't know if Gary's here. Let me see. Yeah, it looks like he's not, but okay, we can look into that. I was not aware that there was an issue there.
Yeah, and perhaps there are multiple locations to find these simulations, and so maybe we could clear that up and send out a clarification.
Yeah, I guess if whoever brought that up was still here, if you want to maybe either write it in the chat, some more details of specifics of the members that are missing, or send an email.
So I basically looked at I was looking at the SSP5 data set from CSM2 from our System Grid Foundation, where we get the CMIP6 data set. So I realized that there are only 3 ensemble members in that scenario. So I was hoping that there are more. If there are, how can I get that?
I believe there might only be 3. I don't know. Nan, do you know?
I'm sorry. I wasn't following the conversation up this moment. Can you repeat the question?
Yeah. So the question is, are there more than 3 CMIP6 SSP585 members? I thought there was 3, but
I believe there's only 3. Let me double check. I'm right there to do that.
Yeah, there's definitely 100 SSP 370s in the large ensemble.
I see.
And there's 16 SSP 245s, but I think we haven't run any extra SSP 585 beyond what was done for CMIP6, and I believe there was only 3. But yeah, maybe Nan can clarify in the chat whenever.
Yeah, there were only 3 of the 585, and those were rerun to fix an issue, but there still remained only 3 corrected simulations for 585.
Thanks. So yeah, I mean, that could be an option if you need more, if we want to explore more scenario space. We have 245, 370. Do we want to expand the 585 simulations? If there's interest in that, that's something we could consider for the next allocation as well.
Great, I'll add that to our group's suggestions, and great, we've solved some problems too. The other thing about data availability were for some simulations that aren't available yet, but will be the mechanically decoupled and the refined grid North Atlantic simulations, and just a general thought that it'd be great if those were made publicly available. And I believe both are expected to become so.
Yes, definitely the regionally refined North Atlantic. We've like budgeted the allocation for that in the last proposal, and that will be made available. I guess the mechanically decoupled is a little more tricky for us just because it was not working group resources. But if you have resources on your side to kind of make that available, then at least there's a portion of it could be made available as well.
Yeah, we've been working with Gary to reduce as much as possible, even just the main, the big variables, and ignore a lot of the others and shrink it down to maybe just a couple terabytes, is very, very much within reasonable expectations. And so the other suggestions for potential future simulations, one was, I think, sort of motivated by one of the talks this morning, which was the ozone single forcing experiments with just stratospheric ozone forcing, just tropospheric ozone, and then a combination of both would be interesting to be run. Another suggestion was an ensemble with different aerosol emissions or different aerosol cloud interaction parameters. It was something to investigate or the model sensitivity to aerosols in CESM2. And then finally, it was related to the high resolution pre-industrial control run and a question if that could be extended to be a longer run in the future as well.
That is that the CSM1 IHESP?
I think so. We kind of switched out of breakout groups before that could be fully clarified. Oh, there's a message in the chat.
Yeah, I think I was talking about like the CSM2. I mean CSM1. Sorry, CSM1. Like the IHESP version. Like there is like currently 500 years of the high resolution, and it would be great if it can be extended for longer. Yeah, thanks.
I can try to answer that. So the IHESP simulation may actually have extended somewhat beyond 500. I think they might have actually gone out to 650, but that was run on the machines in China, which is the Sunway system. It wasn't run on any system in the US. And I don't believe that we have the restarts for that or the ability to run that in the same, it would be a major machine change to continue that run. That would be a science question, whether that would be a valid extension of that simulation.
I see. Thank you so much.
Thanks. So is that was that the summary from? Was there anything else to add, Sarah?
Oh no, that's it.
Okay, cool. Yeah, I think also we should think more about single forcing runs too. There's going to be this WCRP single forcing large ensemble MIP, which is asking for quite a lot of different forcings. We have some of them already, but we should think about whether we want to contribute other ones. I don't have the list with me right now, but I'm not sure how interesting all of them will be, but we could think about whether we want to add any more of those, and that the ozone forcing would come into that, as well as like volcanoes only, and yeah, I don't remember the rest. So we could just have an open discussion now if anyone has any thoughts. I guess Brian, you posted something about a PPE in the chat that was for Cam, or is that for coupled simulations?
It's Cam only, and they're short runs, and they're focused on perturbing parameters that are in the convection, cloud, and microphysics schemes. And it sounded like what one of the questions that from Sarah's group was about that topic. So I thought I would share that there is this PPE available, and I think it'll be made public imminently. I mean, very soon, if it's not already public.
Okay, excellent. Yeah, I think it was Hansi's suggestion for the PPE for coupled, particularly focused toward the Labrador sea freezes. Yeah, I certainly don't have enough knowledge to suggest anything that exactly how that would go, but
that would be a more expensive PPE.
Yeah. So does anyone have anything else that they didn't get a chance to bring up in the breakout rooms? Any experiments that you'd like to see done in the next 2 years? We'll send out this Google Doc to the mailing list so you can think about it some more and put in any ideas that you like. And obviously, if you have a suggestion and you want to take the lead on it, that you're very welcome to do that. So it's not like you're suggesting experiments that other people we'll be doing. You can take the lead on things if you suggest them. All right, it looks like maybe that's all for today. Unless it's Sarah or Aishu, do you have anything else to add?
No, just thanks for the great talks. A lot of kind of illuminating ideas about the high latitudes, which was nice to see everything kind of together like that.
Yeah. Great. Well, we hope we'll be seeing you in person next time. Thank you all for joining. And thanks for the talks. All right. See you.
Bye.
Bye.
Bye.